Hello and welcome. I'm so glad you're here with me tonight as we begin a journey through one of the universe's most profound transformations. Get comfortable, take a deep breath, and let's explore together what happens after a star dies. Right now, at this very moment, somewhere in our galaxy, a star is experiencing its final heartbeat. In about 8 minutes, the light from that dying moment will reach us, carrying the story of a cosmic death that's been billions of years in the making. But here's what keeps astronomers awake at night. That star has known it was dying for thousands of years before this final moment, and it's been screaming warnings into space that we're only just learning to hear. If you're fascinated by the mysteries of the cosmos and want to join us on more journeys like this, I'd love for you to hit that subscribe button and give this video a like. It truly helps us reach more curious minds like yours, and it lets me know you'd like more deep dives into the wonders of our universe. Now, imagine being a star. For millions or even billions of years, you've been the picture of stability, fusing hydrogen into helium in your core, maintaining a perfect balance between the crushing inward pull of your own gravity and the outward pressure of nuclear fusion. It's a tightrope walk that's lasted longer than human civilization has existed, longer than complex life has crawled across Earth's surface. But then something shifts. Something fundamental changes in your core, and suddenly, you know your time is running out. This is where our story truly begins, because stars don't die quietly or without warning. They put on a spectacular show, and if you know what to look for, you can read the signs of their approaching end written across the cosmos. Let's start with what actually happens inside a dying star. For most of a star's life, it's engaged in a cosmic balancing act. In the core, hydrogen atoms are being crushed together with such force that they overcome their natural repulsion and fuse into helium, releasing tremendous amounts of energy in the process. This energy creates an outward pressure that counteracts gravity's relentless inward pull. It's like an eternal arm wrestling match where neither side can win, and that stalemate is what we call a star's main sequence life. Our sun has been in this phase for about 4.6 billion years and has another 5 billion years to go. But here's the cruel reality of stellar physics. Hydrogen doesn't last forever. When a star begins to run low on hydrogen fuel in its core, the nuclear fusion reactions start to sputter and weaken. With less outward pressure to resist gravity, the core begins to contract. And here's where it gets fascinating. This contraction actually heats up the core, eventually reaching temperatures high enough to fuse helium into carbon and oxygen. The star has found a new fuel source, but there's a catch. This new phase is far less stable. For massive stars, those at least 8 times the mass of our sun, this is just the beginning of a desperate struggle. They'll move through fuel after fuel, helium, carbon, neon, oxygen, silicon, each burning faster than the last. A star might spend 10 million years burning hydrogen, but only burns silicon for a matter of days before the end comes. It's like watching someone sprint through their savings after losing their job. Each dollar spent faster than the last. But how do we actually observe these changes? How do astronomers know when a star is entering its death throes? This is where modern astronomy becomes absolutely fascinating. One of the most dramatic examples we've witnessed in recent years is Betelgeuse, the bright red supergiant that marks Orion's shoulder. Between late 2019 and early 2020, Betelgeuse dimmed dramatically, losing more than half its brightness. For astronomers, this was electrifying. Was this the sign that Betelgeuse was about to explode as a supernova? Telescopes around the world and in space turned their attention to this star. What we learned was extraordinary. High-resolution imaging revealed that Betelgeuse had ejected a massive amount of material from its surface, creating a dust cloud that temporarily blocked our view of the star. This wasn't the supernova we were hoping to observe, but it was something equally revealing. We were watching a star in its death throes, literally throwing off parts of itself into space. Betelgeuse is unstable, pulsating, changing brightness, and experiencing massive convection currents that bring material from deep inside up to the surface. These are all signs of a star that has exhausted its core hydrogen and is now burning heavier elements in shells around its core. Think about that for a moment. We can watch a star that's 550 light years away, so distant that the light we're seeing left that star during the Renaissance, and we can detect changes in its brightness, analyze the spectrum of its light, and determine that it's in the late stages of its life. That's not just observation. That's reading a stellar death certificate in real time. Now, different mass stars show different symptoms as they approach death. And understanding these differences is crucial to grasping what happens after they die. Let me walk you through this, because it's one of the most elegant pieces of stellar physics. Low-mass stars like our Sun, those between about 0.8 and 8 solar masses, have a relatively gentle decline. As they run out of hydrogen, they expand into red giants, their outer layers swelling to enormous sizes. Our Sun will eventually expand beyond Earth's orbit. During this phase, they become unstable, pulsating variables that change in brightness over periods of months or years. They'll shed their outer layers in gentle waves, creating beautiful planetary nebulae, those stunning cosmic butterflies we see through telescopes. The core that's left behind becomes a white dwarf, a Earth-sized ember that will cool slowly over trillions of years. But massive stars? They're in a completely different category. Stars above 8 solar masses have enough gravitational pressure to fuse elements all the way up to iron. And here's where we hit a fundamental wall of physics. Fusing iron doesn't release energy, it absorbs energy. When a massive star's core turns to iron, fusion stops dead. There's no more energy being produced to hold up the star against gravity. What happens next occurs faster than you can blink. Within about 1 second, the iron core, roughly the size of Earth but containing more mass than our Sun, collapses. Electrons are crushed into protons, creating neutrons and releasing a flood of neutrinos. The core becomes so dense that the collapsing material literally bounces off it, creating a shock wave that tears the star apart in a supernova explosion so bright it can briefly outshine an entire galaxy. The signs that this is about to happen are subtle but detectable. Massive stars in their final years show erratic brightness changes. Their spectra reveal they're enriched with heavy elements dredged up from their cores. They often develop strong stellar winds, blowing off material at speeds of thousands of kilometers per second. Some develop thick circumstellar shells of gas and dust from previous mass loss events. One of the most important signs is spectral changes. When astronomers analyze the light from a star, breaking it down into its component wavelengths, they can identify which elements are present in the star's atmosphere. A star approaching death will show increasing amounts of helium, carbon, nitrogen, and oxygen, the fusion products being mixed up from the core. In the most massive stars, we can even detect signs of silicon and sulfur, elements that form just before the final iron core develops. There's also the fascinating case of luminous blue variables, or LBVs. These are extremely massive stars, 50 to 100 times the mass of our Sun, that undergo dramatic eruptions, suddenly brightening and ejecting huge amounts of material. Eta Carinae, one of the most massive star systems in our galaxy, underwent such an eruption in the 1840s, briefly becoming the second brightest star in the night sky. That eruption ejected more than 10 times the mass of our Sun. These events are thought to be signs of internal instability as the star burns through its nuclear fuel at a prodigious rate. Here's a question worth pondering. How much warning would we get if a nearby star was about to explode as a supernova? The answer is both comforting and unsettling. For the truly catastrophic effects, a supernova would need to be within about 25 light-years of Earth. Thankfully, there are no stars the mass of that close to us. Betelgeuse, our best candidate for the next visible supernova, is far enough away that we'd be treated to a spectacular light show without any danger. But the warning signs, they'd be visible for centuries or millennia before the actual explosion. The star would be brightening, dimming, changing color, ejecting shells of material, all visible to our telescopes. One common misconception I want to address is the idea that stars explode because they run out of fuel. That's not quite right. Low-mass stars do essentially run out of fuel, but they don't explode. They just gently shed their outer layers. Massive stars don't run out of fuel in the sense of having nothing left to fuse. They run out of fuel that releases energy when fused. Iron is the problem, not the absence of material. Another mistake people often make is thinking that a star's death is instantaneous. The actual supernova explosion happens incredibly quickly, yes, but the dying process, that takes time. A massive star might spend 90% of its life peacefully fusing hydrogen, then rush through helium fusion in 1,000,000 years, carbon fusion in 1,000 years, and silicon fusion in a few days before the final collapse. It's not a switch being flipped, it's a cascade of increasingly desperate attempts to stay alive. There's something deeply moving about understanding stellar death this way. These aren't just balls of gas exploding. They're complex systems fighting against inevitable thermodynamic fate, finding new ways to generate energy, restructuring themselves, holding on for as long as physics will allow. And in their final moments, they create the very elements that make life possible. Every iron atom in your blood was forged in the core of a dying massive star. The calcium in your bones, the oxygen you're breathing right now, the carbon that forms the backbone of every molecule in your body, all of it was created in stellar furnaces and scattered into space when those stars reach their point of no return. We've established what happens as a star approaches death. These dramatic changes in behavior that serve as cosmic warning signs. But what happens in those final moments when the point of no return is reached? What does it actually look like when a star crosses that threshold? That's where our journey takes us next, into one of the most spectacular phenomena in the universe, the supernova itself, and the incredible history of how humans have observed these stellar explosions across millennia. On July 4th, 1054, Chinese astronomers looked up at the night sky and witnessed something that would challenge everything they understood about the heavens. A new star had appeared, so bright it was visible in broad daylight for 23 days straight. It outshone every object in the sky except the sun and moon. They called it a guest star, meticulously recording its position in the constellation we now know as Taurus. What they were actually witnessing was a star located 6,500 light-years away, tearing itself apart in one of the most violent events in the universe, a supernova explosion. And here's what makes this absolutely mind-bending. That explosion had actually happened 6,500 years earlier, during the dawn of human civilization, and its light was only just reaching Earth in 1054. If you're captivated by these cosmic stories and want to continue exploring the universe's greatest mysteries with me, please take a moment to like this video and subscribe. Your support means the world and helps us create more content diving deep into the wonders of space and time. Now, what makes supernovae so extraordinary isn't just their brightness, though that is staggering. A single supernova can briefly shine with the luminosity of 5 billion suns. Think about that. One dying star for a few weeks can output as much light as an entire galaxy of hundreds of billions of stars. But beyond the spectacle, Supernovae represent something far more profound. They are the universe's great recycling program, the cosmic factories that forge the heavy elements necessary for planets and ultimately for life itself. Let me take you on a journey through the most significant supernova observations in human history, because each one taught us something revolutionary about the cosmos and our place within it. That 1054 event I mentioned, the one observed by Chinese astronomers, has a modern identity. Today, we call the remnant of that explosion the Crab Nebula, and it's one of the most studied objects in astronomy. When astronomers in the 1700s first observed this nebulous patch of light through telescopes, they had no idea what they were looking at. It wasn't until the 1900s that we connected the dots between the Chinese historical records and this expanding cloud of gas. But here's what makes the Crab Nebula absolutely fascinating. At its center sits a pulsar, a rapidly spinning neutron star that rotates 30 times per second, beaming radiation across space like a cosmic lighthouse. This isn't just a dead star's remnant. It's an incredibly dense object, containing more mass than our entire sun, compressed into a sphere just 20 kilometers across. Every time that pulsar spins, we can detect its pulse, a cosmic heartbeat that has been beating for nearly 1,000 years since we first witnessed its birth. The Chinese weren't the only ones to document this event. Native American rock art in what is now New Mexico and Arizona also depicts a bright star near the crescent moon, dating to exactly the same period. Indigenous peoples on opposite sides of the planet, with no contact with each other, both looked up and recorded this cosmic explosion. It's a powerful reminder that humanity's fascination with the night sky transcends culture and geography. But while the 1054 supernova was meticulously recorded in the East, European records from that period make no mention of it whatsoever. Why? This is where the story gets fascinating from a historical perspective. Medieval Europe was deeply influenced by Aristotelian philosophy, which held that the heavens were perfect, unchanging, and eternal. The appearance of a new star would have been philosophically problematic, perhaps even heretical. It's possible that European scholars simply chose not to record something that contradicted their worldview. This is a crucial lesson that echoes through scientific history. Sometimes we don't see things not because they're not there, but because we're not looking, or because we're afraid of what we might find. Fast forward to November 11th, 1572. The Danish astronomer Tycho Brahe was walking home from his laboratory when he noticed something impossible in the constellation Cassiopeia, a brilliant new star where none had existed before. Unlike his medieval predecessors, Tycho didn't dismiss what he saw. He observed it meticulously for months, measuring its position with unprecedented precision for that era. This observation was revolutionary, and here's why. Tycho proved that this new star showed no parallax, meaning it wasn't moving relative to the background stars as Earth orbited the Sun. This placed the new star far beyond the moon, out in what was supposed to be the unchanging celestial realm. With this single observation, Tycho shattered the Aristotelian model of perfect, immutable heavens. The universe could change, stars could appear and disappear. The cosmos was dynamic, not static. Tycho's supernova, as we now call it, was so bright that it was visible during the day, and at its peak, it rivaled Venus in brightness. We now know it was a type Ia supernova, a specific kind of explosion that occurs when a white dwarf star accumulates too much mass from a companion star and undergoes a thermonuclear detonation. The remnant of Tycho's supernova is still visible today through X-ray telescopes, an expanding shell of debris traveling at 5,000 kilometers per second. What I find personally moving about Tycho's story is his courage to trust his observations over established dogma. In an age when questioning celestial perfection could be dangerous, he published his findings in a book called De Nova Stella, on the new star, literally giving us the word nova that we still use today. Science progresses not just through discovery, but through the bravery to report what we actually see, even when it contradicts what we've been taught to believe. Just 32 years later, in October 1604, another brilliant star appeared, this time in the constellation Ophiuchus. The German astronomer Johannes Kepler observed and documented this supernova extensively. Like Tycho's supernova, Kepler's new star was visible in daylight and remained visible to the naked eye for over a year. It reached a magnitude that made it the second brightest object in the night sky after Venus. Kepler's work on this supernova built upon Tycho's legacy, further cementing the understanding that the heavens were not immutable. But here's what makes Kepler's supernova particularly significant. It was the last supernova visible to the naked eye in our Milky Way galaxy. That was 420 years ago. We are, statistically speaking, overdue for another one. Astronomers estimate that supernovae should occur in a galaxy like the Milky Way, about once every 50 to 100 years. We've gone 4 times that long without a visible one. Where are they? This is one of astronomy's intriguing mysteries. We know supernovae are still happening in our galaxy. We've detected their remnants using radio and X-ray telescopes, but they're occurring in regions obscured by dust, or on the far side of the galactic center where we can't see them directly. The galaxy is conspiring to hide its spectacular deaths from us. Imagine for a moment what it would be like if a supernova exploded in our galactic neighborhood today. Unlike Tycho and Kepler, who had only their eyes and basic instruments, we have an entire arsenal of observational technology: space telescopes, gravitational wave detectors, neutrino observatories, radio telescope arrays spanning continents. We would capture this event across the entire electromagnetic spectrum and beyond, gathering more data in the first hour than Tycho and Kepler collected in their lifetimes. It would be the most closely studied astronomical event in human history. And then, after centuries of waiting, came February 23, 1987. Astronomers in the southern hemisphere noticed a new bright star in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of about 160,000 light-years. This was SN 1987A, and it changed everything about how we study supernovae. For the first time in human history, we observed a supernova not just with optical telescopes, but with neutrino detectors. About 3 hours before the light from the explosion reached Earth, neutrino detectors in Japan and Ohio registered a burst of neutrinos, ghostly particles that barely interact with matter and can pass through entire planets as if they weren't there. These neutrinos had escaped from the collapsing core of the dying star and raced toward Earth at nearly the speed of light. Let me pause here because this is profound. Neutrinos reached us before the light did because they escaped from the star's core immediately when it collapsed, while the light had to fight its way out through thousands of kilometers of dense stellar material. We literally detected the moment of core collapse, the instant when the star's heart turned into a neutron star, before we even saw the explosion itself. This was like hearing someone's last heartbeat 3 hours before witnessing them fall. The detection of neutrinos from SN 1987A confirmed decades of theoretical predictions about how massive stars die. It proved that our models of stellar collapse were fundamentally correct. We predicted neutrinos would be released in this exact way, with this approximate energy, and there they were, arriving from 160,000 light-years away, right on schedule. But SN 1987A held more surprises. The star that exploded was identified in pre-explosion photographs as Sanduleak 6902, a blue supergiant. This was unexpected. Theory predicted that stars should expand into red supergiants before exploding. Yet here was a blue supergiant going supernova. This forced astronomers to revise their models, to understand that stellar evolution can take unexpected paths depending on a star's mass, composition, and whether it's part of a binary system. Over the following years and decades, astronomers watched as the debris from SN 1987A expanded outward, crashing into material the star had ejected earlier in its life. This collision heated the gas, creating a glowing ring that has become one of astronomy's most iconic images. The Hubble Space Telescope has monitored this ring for decades, watching it brighten and fade as shock waves race through it, creating what looks like a cosmic string of pearls expanding through space. Here's what keeps astronomers excited about SN 1987A even today. Somewhere in the center of that expanding debris cloud, there should be a neutron star, or possibly even a black hole, the collapsed core left behind when the outer layers exploded. But we haven't found it yet. The debris is still too thick, obscuring our view. It's like knowing there's a treasure buried somewhere, having a map, but having to wait years for the dust to settle before you can dig. When we finally detect that central object, whether through X-rays, radio waves, or infrared light penetrating the debris, it will be another triumph of astronomical patience and persistence. One crucial lesson from these historical observations is how much timing matters in astronomy. If Tycho had been looking the other direction that November evening, if Kepler had been too busy with his calculations to observe the night sky, if the neutrino detectors hadn't been operational in February 1987, we would have missed crucial data. Astronomy is often about being ready for the universe's surprises, about having instruments operating and astronomers watching when cosmic events unfold according to their own schedule, not ours. Another common misconception I want to address. Many people think supernovae are rare. They're not. They're just rare in any given galaxy. Across the entire observable universe, several supernovae are exploding every second. Every time your heart beats, multiple stars are dying in catastrophic explosions across the cosmos. We discover thousands of supernovae every year in distant galaxies, each one a laboratory for understanding stellar physics, cosmic distances, and the evolution of the universe itself. In fact, Type Ia supernovae, those thermonuclear explosions of white dwarf stars, have become one of astronomy's most important tools. Because these explosions are remarkably consistent in their brightness, they serve as standard candles for measuring cosmic distances. It was by studying distant Type Ia supernovae in the 1990s that astronomers discovered the universe's expansion is accelerating, driven by something we call dark energy. 3 scientists won the Nobel Prize in Physics in 2011 for this discovery. Stellar deaths aren't just spectacular, they're fundamental tools for understanding the entire universe. Have you ever wondered what it would actually look like if you could watch a supernova from a safe distance, say a few light years away? You'd first see the star brightening rapidly over a few hours, its luminosity increasing by a factor of billions. The initial light would be mostly blue and ultraviolet, intensely hot. Over days and weeks, the color would shift toward red as the expanding debris cooled. And if you had eyes sensitive to X-rays and gamma rays, you'd see something even more spectacular. Jets of high-energy radiation beaming out from the explosion, accelerating particles to nearly the speed of light. The shock wave itself would be visible as it plowed through any surrounding gas, lighting it up like a cosmic neon sign. The question that connects all these historical observations is this: what do these violent stellar deaths create? When a star explodes with such tremendous force, scattering its material across light years of space, what legacy does it leave behind? The answer transforms everything we understand about our own existence. Because in the heart of those explosions, in the intense heat and pressure of a star's final moments, something remarkable happens. The universe manufactures the raw materials of worlds and life itself. And understanding exactly how that works, how stellar death becomes the seed of future creation, that's where our journey takes us next. Take a moment right now and hold out your hand. Look at it. The iron flowing through your bloodstream at this very moment, carrying oxygen to every cell in your body, was forged inside a star that exploded billions of years ago, long before our sun even existed. The calcium strengthening your bones right now was created in the final minutes of a dying star's life. And the gold in any jewelry you might be wearing, that required something even more violent. The collision of two dead stars smashing together with such force that it literally warped the fabric of space-time. You are not just made of star stuff, as Carl Sagan famously said. You are made of dead star stuff. You are assembled from the ashes of cosmic catastrophes. If this connection between stellar death and your own existence fascinates you, I'd be honored if you'd subscribe to this channel and leave a like on this video. It helps us reach others who are curious about their cosmic origins, and it lets me know you want to explore more of these profound connections. Now, let me explain something that fundamentally changed how we understand both stars and ourselves. The discovery of stellar nucleosynthesis, the process by which stars create elements. This story begins in 1946, in the aftermath of World War II, when a British astronomer named Fred Hoyle began asking a question that seems almost childishly simple. Where do chemical elements come from? At the time, most scientists believed that all elements were created in the Big Bang, but Hoyle recognized a problem with this idea. The Big Bang could explain hydrogen and helium, the two lightest elements, but it couldn't explain everything else. The conditions in the early universe weren't right to forge heavy elements in significant quantities. There had to be another forge, another factory. And Hoyle realized what it was: stars. Working with colleagues Margaret Burbidge, Geoffrey Burbidge, and William Fowler, Hoyle developed a comprehensive theory published in 1957 in a landmark paper often called simply B2FH, after the initials of its authors' last names. This paper, running over 100 pages, mapped out exactly how stars create elements through nuclear fusion, step by step, from hydrogen all the way up to iron. But here's where it gets truly fascinating. B2FH showed that stars could create elements up to iron through normal fusion processes during their lives. But what about elements heavier than iron? Gold, platinum, uranium, lead. All the elements above iron on the periodic table. Those require conditions even more extreme than the core of a living star. Those require stellar death. Let me walk you through exactly how this cosmic alchemy works, because it's one of the most elegant processes in all of nature. During a star's normal lifetime, it fuses hydrogen into helium. This is happening in our sun right now, converting about 600 million tons of hydrogen into helium every single second. That process releases energy, which is why the sun shines. When the hydrogen runs low, stars massive enough can fuse helium into carbon and oxygen. Again, this releases energy. As you move up the periodic table, fusing heavier elements together releases less and less energy. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron. And here's where we hit a wall. Iron is the most stable nucleus in nature. Fusing iron into anything heavier doesn't release energy. It requires energy. Iron is the end of the line for normal stellar fusion. But in the intense conditions of a supernova, all bets are off. When the core of a massive star collapses in less than a second, it releases more energy than the star has generated in its entire multi-million-year lifetime. The temperature spikes to billions of degrees. Neutrons, freed from atomic nuclei in the collapsing core, become incredibly abundant. And in this cosmic cauldron, something remarkable happens. Free neutrons start bombarding iron and other nuclei, adding neutrons one by one or in rapid succession. This is called the R process, the rapid neutron capture process, and it's responsible for creating about half of all elements heavier than iron: gold, platinum, iodine, thorium, uranium, all forged in the fury of a supernova. But there's another process, the S process, or slow neutron capture, which happens in the outer layers of red giant stars, including those not massive enough to explode. These aging stars create elements like barium, strontium, and some of the lead in the universe. It's a gentler form of alchemy, taking place over thousands of years as stars slowly shed their outer layers. What I find absolutely stunning is that we can prove this. We can take a meteorite, analyze its chemical composition, measure the ratios of different isotopes, and trace them back to specific nucleosynthesis processes. Some isotopes could only have formed in the R process of a supernova. Others bear the signature of the S process in red giants. Still others came from the Big Bang itself. Every atom tells a story of its origin. In fact, there's a fascinating detective story in Earth's geology. Deep-sea sediments contain a layer enriched in iron-60, a radioactive isotope with a half-life of 2.6 million years. This isotope can only be created in supernovae. The fact that we find it in sediments dating to about 2 to 3 million years ago means a supernova exploded relatively nearby, within about 300 light-years, showering Earth with its debris. Our ancestors, early hominids walking the African savanna, lived through the aftermath of a nearby stellar explosion. They had no idea, of course, but the atoms falling on them had been inside a star just years or centuries earlier. Now, let's talk about spectroscopy, because this is how we know all of this isn't just theoretical speculation. In 1814, a German optician named Joseph von Fraunhofer noticed something strange when he passed sunlight through a prism. The spectrum wasn't a smooth rainbow. It was crossed by hundreds of dark lines. These are now called Fraunhofer lines, and they revolutionized astronomy. Each chemical element absorbs and emits light at specific wavelengths, creating a unique pattern of lines like a barcode. By analyzing the spectrum of light from a star, we can determine exactly which elements are present in its atmosphere and in what proportions. This technique, spectroscopy, allows us to do chemistry on objects trillions of miles away. When we observe the expanding debris from supernova remnants like Cassiopeia A, another supernova remnant from an explosion that occurred around 1680, we can identify iron, silicon, sulfur, calcium, and numerous other elements in the ejected material. We're literally watching the periodic table expand into space. The Chandra X-ray Observatory has mapped the distribution of different elements in this remnant, showing iron concentrated in the center where the star's core was, surrounded by layers of lighter elements. It's like looking at the cross-section of the star at the moment it exploded, frozen in time and space. But here's something that surprised astronomers. When we analyze very old stars, stars that formed in the early universe, we find they have far fewer heavy elements than younger stars like our Sun. This makes perfect sense when you think about it. The first generation of stars formed from the pure hydrogen and helium created in the Big Bang. When those stars died and exploded, they scattered heavier elements into space. The next generation of stars formed from gas clouds enriched with those heavy elements. Each generation of stars adds more heavy elements to the cosmic mix. Our sun is a third-generation star at least, perhaps even fourth or fifth generation. We know this because about 2% of the sun's mass consists of elements heavier than helium, what astronomers call metals, even though they include elements like carbon and oxygen that aren't metals in the chemical sense. Those heavy elements came from previous generations of stars that lived, died, and exploded before our solar system even existed. This means Earth itself, and everything on it, is made from recycled stellar material. When our solar system formed 4.6 billion years ago from a collapsing cloud of gas and dust, that cloud was enriched with the debris from countless stellar deaths. Every element heavier than lithium in your body was created in a star or stellar explosion. Think about the implications for a moment. The oxygen you're breathing right now was created inside a massive star that fused helium in its core, the carbon forming the backbone of every organic molecule in your body came from a red giant star in its death throes. The nitrogen in your DNA was forged in stellar nucleosynthesis. The phosphorus in your bones and teeth likely came from a supernova. You are a walking, breathing museum of stellar archaeology. Carl Sagan popularized the phrase, "We are made of star stuff," in his 1980 series Cosmos. But the full truth is even more poetic. We are made of dead star stuff. We are made of the ashes of ancient suns, atoms that have been recycling through the cosmos for billions of years, passing through multiple generations of stars before finally assembling into the planets and life forms we see today. And it's not just the common elements. Consider gold for a moment. Gold is created primarily in the R process during neutron star mergers or certain types of supernovae. Every gold atom on Earth was created in a violent cosmic event. The gold in any ring, coin, or electronic device existed inside a dying star billions of years ago. In a very real sense, we treasure gold not just for its rarity and beauty, but because each atom represents a stellar catastrophe. In 2017, astronomers detected gravitational waves from two neutron stars colliding 130 million light-years away in the galaxy NGC 493. Telescopes around the world immediately swung into action, and they observed something extraordinary, the optical and infrared signature of heavy element creation in real time. This collision, which lasted just milliseconds, created an estimated 10 to 20 times the mass of Earth in pure gold, along with vast quantities of platinum, uranium, and other heavy elements. This single event may have produced more heavy elements than the Sun will produce in its entire 10 billion year lifetime. This observation solved a long-standing mystery. While we knew supernovae could produce some heavy elements through the R process, the numbers didn't quite add up. There's more gold and platinum in the universe than supernovae alone could explain. Neutron star mergers fill that gap. These collisions are rarer than supernovae, but they're incredibly efficient at producing heavy elements. Current estimates suggest that most of the gold and platinum in the universe, including the gold in any jewelry you own, came from neutron star collisions. Let me address a common misconception here. Some people think that because we're made of elements created in stars, we're somehow less special or less significant. I see it exactly the opposite way. The fact that stars had to live and die to create the elements necessary for life makes us part of a cosmic story billions of years in the making. The atoms in your hand are older than the Earth itself. They've been through stellar cores, supernova explosions, interstellar space, the formation of our solar system, the geological evolution of Earth, and countless biological cycles before becoming part of you. That's not diminishing, that's profound. Another misconception is that all heavy elements came from one type of source. The reality is far more nuanced. Oxygen comes primarily from massive stars that end as supernovae. Carbon comes from both massive stars and intermediate mass stars that don't explode but gently shed their outer layers. Nitrogen has a complex origin involving both types of stars, plus additional processing in the interstellar medium. Iron comes mainly from type Ia supernovae, those thermonuclear explosions of white dwarfs. Gold and platinum come primarily from neutron star mergers. Lithium, beryllium, and boron are created when high-energy cosmic rays smash into heavier atoms in space, breaking them apart. The periodic table is a catalog of different stellar processes and cosmic events. Here's a question worth contemplating. Could life exist without stellar death? The answer is almost certainly no. Life as we know it requires complex chemistry, which requires a diverse palette of elements. Hydrogen and helium alone can't create the molecular complexity necessary for self-replicating systems, for information storage, for the chemical reactions that power metabolism. We need carbon, nitrogen, oxygen, phosphorus, sulfur, and trace amounts of many other elements. All of those came from stellar nucleosynthesis and stellar death. This means that every living thing on Earth exists only because uncountable stars lived, died, and scattered their enriched material into space over billions of years. The atoms in the hemoglobin carrying oxygen in your blood were once in the core of a massive star. The calcium in your bones was ejected from a dying red giant. The trace elements essential for your biology, elements like zinc, copper, selenium, and iodine, all have stellar origin stories. And this process is still happening. Right now, stars are dying throughout the universe, enriching the interstellar medium with heavy elements. Somewhere, perhaps in a galaxy millions of light years away, a cloud of gas enriched by recent supernovae is beginning to collapse, forming new stars and planets. Perhaps billions of years from now, life will arise on one of those planets, life made possible by the stellar deaths happening at this very moment. The cosmic supply chain from stellar death to new life is elegant in its circularity. Stars create heavy elements. They die, scattering those elements into space. New stars and planets form from that enriched material. On some planets, conditions allow those elements to organize into increasingly complex molecules. Eventually, if conditions are right and enough time passes, those molecules become self-replicating, information-storing systems. Life emerges. That life eventually develops intelligence and consciousness. And that consciousness, billions of years after the stellar deaths that made it possible, looks up at the night sky and wonders about its origins. We are the universe becoming aware of itself, to paraphrase Carl Sagan again. We are atoms arranged in such a way that we can contemplate atoms. We are star stuff that has evolved to study stars. But while massive stars explode spectacularly, scattering their materials far and wide, not all stars meet such violent ends. Some stars, those more similar to our own sun, take a gentler path toward their final rest. Understanding this quieter form of stellar death reveals a different but equally beautiful chapter in the story of how stars return their matter to the cosmos. In about 5 billion years, our sun will swell into a red giant so enormous that its outer layers will engulf Mercury, Venus, and possibly Earth itself. But it won't explode. Instead, it will gently puff off its outer atmosphere into space, creating a beautiful glowing shell of gas, and leave behind a glowing ember about the size of Earth, but containing 60% of the sun's original mass. That ember, called a white dwarf, will be so dense that a single teaspoon of its matter would weigh about 15 tons on Earth. And here's what's truly extraordinary. That white dwarf will remain hot, gradually cooling over trillions of years, potentially outlasting every other type of star in the universe. This is the fate awaiting the vast majority of stars, including our own sun. Not a bang, but a long, dignified fade into cosmic darkness. If you're finding beauty in these gentler stellar endings, please consider subscribing and giving this video a like. Your engagement helps us continue exploring the full spectrum of cosmic phenomena, from the explosive to the serene. The story of white dwarfs begins in 1844 with one of astronomy's most famous stars, Sirius, the dog star, the brightest star in our night sky. The German astronomer Friedrich Bessel noticed something peculiar about Sirius. It was wobbling. As it moved through space, it wasn't traveling in a straight line, but rather in a slight wave pattern, as if something invisible was tugging on it gravitationally. Bessel proposed a radical idea. Sirius had an invisible companion star orbiting it. This companion would have to be massive enough to influence Sirius's motion, but somehow too faint to see, even though Sirius itself was brilliantly visible. For 18 years, astronomers searched for this invisible companion, and in 1862, the American telescope maker Alvin Graham Clark finally spotted it while testing a new telescope. There it was, a faint point of light right next to blazing Sirius. But when astronomers measured this companion star, which we now call Sirius B, they encountered something that seemed to violate the laws of physics. Based on its gravitational influence on Sirius, Sirius B had to be almost as massive as the Sun. Yet it was incredibly faint and appeared to be very small. The implications were staggering. Here was an object with roughly the Sun's mass compressed into something the size of Earth. The density was incomprehensible by any physics known at the time. For decades, Sirius B remained an astronomical enigma. How could matter be compressed to such extreme density? What was preventing it from collapsing further under its own gravity? The answer wouldn't come until the development of quantum mechanics in the 1920s. An Indian physicist named Subramanian Chandrasekhar, while sailing from India to England in 1930 at just 19 years old, worked out the physics of white dwarfs during the voyage. He realized that white dwarfs are supported not by thermal pressure like normal stars, but by something called electron degeneracy pressure, a purely quantum mechanical effect. Here's how it works, and this is where physics becomes almost magical. According to the Pauli exclusion principle, a fundamental law of quantum mechanics, no two electrons can occupy the exact same quantum state. When you compress matter to white dwarf densities, the electrons are forced into higher and higher energy states because all the lower states are already occupied. This creates a pressure that has nothing to do with temperature. Even a completely cold white dwarf would still have this degeneracy pressure supporting it against gravity. Chandrasekhar also made another crucial discovery that would eventually win him the Nobel Prize in 1983. There is a maximum mass limit for white dwarfs. If a white dwarf accumulates more than about 1.4 times the Sun's mass, electron degeneracy pressure can no longer support it, and it will collapse. This is called the Chandrasekhar limit, and it has profound implications for understanding stellar evolution and supernova explosions. But let me paint you a clearer picture of just how bizarre white dwarfs really are. Imagine taking the entire mass of the Sun and crushing it down until it fits inside a sphere roughly the size of Earth. The density would be approximately 1 million times that of water. A sugar cube-sized piece of white dwarf material would weigh about the same as an elephant. The gravitational field at the surface would be about 350,000 times stronger than Earth's gravity. If you could somehow stand on the surface of a white dwarf, you'd be instantly flattened into a layer of atoms just a few atoms thick. The atoms themselves are crushed together so tightly that the normal structure of matter breaks down. In normal matter, atoms are mostly empty space. The nucleus occupies a tiny fraction of the atom's volume, with electrons orbiting in the vast space around it. But in white dwarf matter, the atoms are pressed together so closely that the electron clouds overlap and merge into what's called a degenerate electron gas. The atomic nuclei are still there, mostly carbon and oxygen in white dwarfs formed from stars like our Sun. But they're floating in this sea of quantum mechanically pressurized electrons. And here's something that confused scientists for years. White dwarfs are hot when they form, with surface temperatures often exceeding 100,000 Kelvin, far hotter than the sun's surface. Yet, they're not generating any energy through fusion. They're not burning anything. They're simply radiating away the residual heat from their formation. They're like cosmic embers, slowly cooling over immense spans of time. How long does it take a white dwarf to cool? This is where the timescales become truly astronomical. A white dwarf will take about 10 billion years, longer than the current age of the universe, just to cool to a temperature where it would appear red rather than white. To cool completely to the background temperature of space would take trillions of years. The universe itself is only 13.8 billion years old, so there hasn't been enough time for any white dwarf to cool completely. Every white dwarf that has ever formed is still glowing, still radiating heat into space. In 2019, astronomers made a discovery that sounds like something from science fiction, but is absolutely real. White dwarfs are slowly crystallizing into giant cosmic diamonds. Let me explain this remarkable finding. As a white dwarf cools, the carbon and oxygen nuclei in its interior slow down. Remember, temperature is just a measure of how fast particles are moving. As these nuclei cool and slow, they eventually reach a point where the electromagnetic forces between them cause them to lock into a crystalline lattice structure, just like carbon atoms forming diamond here on Earth. Except, this is happening on a stellar scale, in an object containing about 60% the mass of our Sun. Astronomers at the University of Warwick analyzed data from the Gaia Space Telescope, which has measured the positions and brightnesses of over 1 billion stars. They found that certain white dwarfs appeared to be cooling more slowly than expected. The reason? As the interior crystallizes, it releases latent heat, the same phenomenon that keeps water at 0 degrees Celsius as it freezes into ice, even though you're removing heat from it. This crystallization process slows the cooling by about 2 billion years. This means that scattered throughout our galaxy are objects that appear to be glowing spheres, but are actually mostly solid crystal in their interiors, giant diamonds floating through space. When our Sun becomes a white dwarf in about 5 billion years and then spends another 10 billion years cooling, its core will eventually crystallize. Our Sun's ultimate fate is to become a diamond the size of Earth. But white dwarfs aren't just fascinating objects in themselves. They're crucial tools for understanding the universe. Let me tell you about one particularly important application. When a white dwarf is part of a binary system, orbiting another star, something dramatic can happen. If that companion star is close enough, the white dwarf's intense gravity can pull material from the companion onto itself. This stolen material accumulates on the white dwarf's surface, getting compressed and heated by the intense gravity. Eventually, this accumulated hydrogen undergoes fusion in a runaway thermonuclear reaction, creating what we call a nova, a sudden brightening that can make the system thousands of times more luminous for a few days or weeks. But if the white dwarf keeps accumulating mass and approaches the Chandrasekhar limit of 1.4 solar masses, something even more spectacular happens. The entire white dwarf undergoes a thermonuclear detonation, a type Ia supernova. These explosions are remarkably consistent in their brightness because they all occur when a white dwarf reaches the same critical mass. This consistency makes them standard candles for measuring cosmic distances. It was by studying distant type Ya supernovae in the 1990s that two teams of astronomers independently discovered that the universe's expansion is accelerating. Distant supernovae appeared slightly fainter than expected, which meant they were farther away than expected, which meant the universe's expansion was speeding up rather than slowing down. This discovery led to the inference of dark energy and earned the Nobel Prize in Physics in 2011. White dwarfs, these quiet stellar remnants, became key to understanding the fate of the entire universe. Let me address a common misconception about white dwarfs. Many people think they eventually burn out and go dark. This isn't quite accurate. White dwarfs don't burn anything. They're not undergoing fusion. They're simply cooling, radiating away stored thermal energy. A better analogy would be a brick taken out of a hot oven. It glows red at first, then gradually cools and darkens. But it's not burning, it's just losing heat. A completely cooled white dwarf, which we call a black dwarf, would still have the same mass and the same structure. It would just be at the temperature of the cosmic background radiation, about 3 Kelvin above absolute zero. However, and this is fascinating, black dwarfs are entirely theoretical. The universe hasn't existed long enough for any white dwarf to cool completely. The coolest white dwarfs we've observed are still radiating at temperatures of a few thousand Kelvin. The first black dwarfs won't form for at least another 100 trillion years, and probably much longer. By that time, the universe will be a vastly different place. All main sequence stars will have long since died, and the cosmos will be entering what's called the degenerate era, dominated by these cooling stellar remnants. Another misconception is that white dwarfs are rare or exotic. In fact, they're the most common stellar endpoint. About 97% of all stars, including our Sun, will end their lives as white dwarfs. Only the most massive stars, those above about 8 solar masses, have enough gravity to collapse beyond the white dwarf stage. This means our galaxy will eventually be populated primarily by white dwarfs. Billions upon billions of slowly cooling Earth-sized embers, each one the compressed core of a star that once shone. One of the most remarkable white dwarfs we know is WD 1145+017, discovered in 2015. This white dwarf shows periodic dips in brightness, and spectroscopic analysis reveals something extraordinary. We're watching a planetary system being destroyed in real time. The white dwarf is surrounded by debris from a disintegrating minor planet, probably something like an asteroid, that's gradually spiraling into the white dwarf and being torn apart by tidal forces. This discovery confirmed something astronomers had suspected. When stars evolve into red giants and then white dwarfs, their planetary systems can survive, at least partially. Some planets are engulfed and destroyed during the red giant phase, but others in wider orbits may survive. Over time, gravitational interactions can cause these surviving planets or smaller bodies to spiral inward, eventually being consumed by the white dwarf. What's particularly poignant is that we can detect the chemical composition of these destroyed worlds. Spectroscopic analysis of white dwarfs with debris disks reveals elements like silicon, magnesium, iron, and calcium, the building blocks of rocky planets. We're essentially performing autopsies on destroyed alien worlds, reading their chemical composition millions or billions of years after they fell into their dying star. In fact, about 25–50% of white dwarfs show evidence of having consumed planetary material. Their atmospheres, which should be pure hydrogen or helium, because heavier elements sink rapidly in the intense gravity, instead show traces of metals. These metals must be constantly replenished by infalling debris. This tells us that planetary systems around white dwarfs are dynamic, chaotic places, with worlds and asteroids gradually spiraling to their doom. Think about what this means for our own solar system's future. When the Sun becomes a white dwarf, Mercury, Venus, and possibly Earth will have been destroyed. But Mars, the asteroid belt, Jupiter, Saturn, and the outer planets will likely survive. Over billions of years, gravitational interactions will gradually perturb some of these bodies into unstable orbits. Eventually, perhaps trillions of years from now, some asteroid or moon will spiral into the white dwarf remnant of our Sun, briefly creating a debris disk as it's torn apart. Any astronomers in the galaxy at that distant time might detect that debris and know that the white dwarf once had planets. Here's a question to consider. Could life exist on planets orbiting white dwarfs? It sounds absurd at first. White dwarfs are so small and dim compared to normal stars, but some astronomers have seriously considered this possibility. A planet would need to orbit very close to the white dwarf to receive enough warmth, perhaps just 1 million kilometers away. At that distance, it would be tidally locked, with one side always facing the star, but the white dwarf would be incredibly stable, shining steadily for billions or trillions of years without the violent changes that affect normal stars. If a planet could survive the red giant phase or form afterwards from debris, and if it ended up in the right orbit, it could potentially remain habitable for longer than any planet orbiting a normal star. There's even a proposal to search for such planets. White dwarfs are common, and a closely orbiting planet would be relatively easy to detect using the transit method, watching for the planet's shadow as it crosses in front of the star. If we found such a planet, it would be one of the strangest potentially habitable worlds imaginable, orbiting a dying star's ember, illuminated by the fading light of stellar death. The story of white dwarfs is ultimately a story of endings and persistence. These objects represent what happens when most stars, after burning through their fuel, can no longer maintain their identity as active stars. They're cosmic monuments to stellar death, yet they persist for timescales that dwarf the age of the universe itself. They're proof that not all endings are violent, that sometimes the universe allows for a gentler transition from life to death. But for those stars too massive to end as white dwarfs, stars whose cores exceed the Chandrasekhar limit, gravity has one more card to play. These stars don't stop at the white dwarf stage. Their cores continue collapsing, crushing matter into a form so dense, so extreme, that it challenges our understanding of physics itself. Let's explore what happens when a stellar core compresses beyond even the impossible density of white dwarfs, into a realm where the very structure of matter fundamentally transforms. Imagine an object so dense that a single grain of sand from its surface would weigh as much as a cruise ship. Imagine a sphere just 20 kilometers across, smaller than Manhattan, yet containing more mass than our entire sun. Imagine a magnetic field so powerful that, from halfway across the solar system, it would erase every credit card on Earth, disrupt every electronic device, and pull the iron from your blood. These objects actually exist. They're called neutron stars, and they represent the absolute limit of how dense matter can become before collapsing into a black hole. They're cosmic laboratories where the laws of physics are pushed to their breaking point, where a single teaspoon of matter weighs 4 billion tons, where gravity is so intense that light itself bends in visible arcs around them. If these extreme cosmic objects fascinate you, I'd truly appreciate you hitting that like button and subscribing to the channel. It helps us reach more people who are curious about the universe's most mind-bending phenomena. The story of neutron stars begins not with their discovery, but with a theoretical prediction that seemed too bizarre to be real. In 1933, just 1 year after the neutron itself was discovered, 2 astronomers at Caltech, Walter Baade and Fritz Zwicky, proposed something radical. They suggested that when massive stars explode as supernovae, they might leave behind a collapsed core made entirely of neutrons. Most physicists dismissed this idea as fantasy. Neutrons were barely understood, and the concept of matter composed purely of neutrons seemed like science fiction. For decades, neutron stars remained a theoretical curiosity, something that might exist in equations but probably not in reality. That all changed on a cold November evening in 1967 at Cambridge University. Jocelyn Bell Burnell, a 24-year-old graduate student, was analyzing data from a radio telescope she had helped build to study quasars. The telescope generated 96 feet of paper charts every day, which Bell examined by hand, looking for signals from distant galaxies. One day, she noticed something strange. A series of regular pulses, beep, 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 appearing at precise intervals of 1.3373 seconds. At first, she and her advisor, Anthony Hewish, thought it might be interference from terrestrial sources, perhaps a car ignition or electrical equipment, but the signal kept appearing at the same spot in the sky, rising and setting with the stars rather than with Earth-based time. It was coming from space. The regularity was so precise, so artificial seeming, that the team half-jokingly called it LGM-1 for Little Green Men 1. Could it be a signal from an alien civilization? Within weeks, Bell discovered 3 more pulsing sources scattered across different parts of the sky. The alien hypothesis became unlikely. It seemed implausible that multiple alien civilizations would all choose to broadcast at these specific intervals and frequencies. But what natural phenomenon could create such precisely timed pulses? The answer came from Thomas Gold at Cornell University. These weren't alien signals. They were rapidly spinning neutron stars. The pulses were caused by the lighthouse effect. As the neutron star spins, beams of radiation from its magnetic poles sweep across space. When one of these beams points toward Earth, we detect a pulse. The neutron star Bell had discovered, now designated PSR B1919+21, was spinning once every 1.3 seconds, acting as the universe's most precise natural clock. Think about what this means physically. An object containing more mass than our sun, compressed into a sphere the size of a city, spinning multiple times per second. The surface of this object is moving at a significant fraction of the speed of light. The equator of a neutron star spinning once per second is traveling at about 20% light speed. That's 60,000 kilometers per second. Nothing made of normal matter could possibly hold together at such speeds. Only the incredible density and gravitational binding of a neutron star makes this possible. Hewish won the Nobel Prize in 1974 for the discovery of pulsars, though controversially, Bell was not included despite being the one who actually discovered them. This became one of the most famous examples of the Matthew effect in science, where credit flows disproportionately to senior researchers. To her credit, Bell has always handled this with remarkable grace, though many in the scientific community consider her one of the most overlooked Nobel-worthy scientists in history. But let's dive deeper into what neutron stars actually are, because the physics is almost unbelievably extreme. When the core of a massive star collapses during a supernova, if the core mass is between about 1, 4 and 3 solar masses, something extraordinary happens. The collapse is so violent that protons and electrons are literally crushed together, combining to form neutrons and releasing floods of neutrinos. The entire core, containing more mass than our sun, collapses from something the size of Earth to a sphere just 20 kilometers across. This happens in less than 1 second. The density becomes incomprehensible. A neutron star contains roughly 500,000 times the mass of Earth, compressed into a sphere that would fit inside a city. The density is approximately 400 trillion times that of water, or about 100 trillion times the density of lead. At this density, atomic structure completely breaks down. Individual atoms cannot exist. Instead, neutrons are packed together so tightly they're essentially touching, supported only by neutron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs but operating at an even more extreme level. The interior structure of a neutron star is something straight out of science fiction, but supported by serious physics. The outer layer, the crust, is about a kilometer thick and is made of atomic nuclei, mostly iron, crushed into a crystalline lattice with free electrons flowing between them. It's similar to white dwarf matter, but even denser. Below the crust is the outer core, where matter becomes so dense that neutrons drip out of nuclei and form a neutron-rich fluid. This is neutron degenerate matter, a quantum fluid unlike anything that exists anywhere else in the universe. Deeper still, in the inner core, we enter a realm of complete uncertainty. At these densities, we're not sure what form matter takes. It might be a soup of free quarks, the fundamental particles that normally exist only inside protons and neutrons. It might contain exotic particles like hyperons or strange matter. We simply don't know because we can't recreate these conditions in laboratories, and our theories become uncertain at these extremes. The magnetic fields of neutron stars are equally mind-boggling. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. When the star's core collapses, any magnetic field present gets compressed along with the matter. And conservation of magnetic flux means the field strength increases dramatically. It's like taking a magnetic field spread over something the size of Earth and crushing it down to city size. The field has nowhere to go but up in intensity. But some neutron stars, called magnetars, have magnetic fields another 1,000 times stronger still, reaching quadrillion times Earth's magnetic field strength. These are the most magnetic objects known in the universe. The magnetic field of a magnetar is so intense that it fundamentally alters the properties of empty space around it, making vacuum behave like a birefringent crystal, splitting light into different polarizations. In December 2004, a magnetar designated SGR 180620, located about 50,000 light-years away on the opposite side of our galaxy, experienced what's called a starquake. The neutron star's crust cracked and shifted, releasing a tremendous burst of gamma rays. This burst, lasting just 1/10 of a second, released more energy than the sun emits in 150,000 years. When the gamma rays reached Earth, traveling for 50,000 years across space, they struck our upper atmosphere with such intensity that they temporarily disrupted the ionosphere, affecting radio communications worldwide. Let that sink in for a moment. An object the size of a city, halfway across the galaxy, had a minor earthquake on its surface, and the energy released was enough to measurably affect Earth's atmosphere from 50,000 light-years away. If that magnetar had been just 10 light-years from Earth instead of 50,000, the gamma-ray burst would likely have caused a mass extinction event, stripping away our ozone layer and exposing the surface to lethal radiation. This event taught us something profound about the danger neutron stars pose, even from vast distances. We worry about asteroid impacts and solar flares, but one of the more exotic existential risks facing Earth is a nearby magnetar outburst. Fortunately, there are no known magnetars close enough to threaten us, but it's a reminder that the universe contains hazards we're only beginning to understand. Now, let me describe what you would experience if you could somehow approach a neutron star. Though I should warn you, this is a journey you would not survive. As you approach from a distance, you'd first notice the incredible speed of the star's rotation. Many neutron stars spin dozens or even hundreds of times per second, the fastest known pulsar, PSR J1748246 AD, spins 716 times per second. The surface is moving at about 25% the speed of light. You'd see the surface as a blur, and if the magnetic poles were pointing your way periodically, you'd see intense beams of radiation sweeping around like a cosmic strobe light. As you got closer, you'd begin to feel intense gravitational effects. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's. This creates extreme gravitational gradients. If you were falling feet first toward a neutron star, the gravity pulling on your feet would be enormously stronger than the gravity pulling on your head. This tidal force would stretch you out long before you reach the surface, a process gruesomely called spaghettification. But even before tidal forces destroyed you, the magnetic field would kill you. The intense magnetic fields near a magnetar would be lethal at distances of 1,000 kilometers or more. At close range, the magnetic field would interfere with the electromagnetic bonds holding atoms together, potentially disrupting molecular structure itself. If you somehow survived all that and reached the surface, you'd find the neutron star's crust is the strongest material in the universe, billions of times stronger than steel. It would have to be, to hold together under such extreme conditions. Standing on the surface, if the word standing even applies, you'd find that the gravity is so intense that the scale height of the atmosphere is measured in centimeters. Any atmosphere, any variation in surface height, is compressed into a layer millimeters thick. Light behaves strangely near neutron stars. The intense gravity bends light rays, meaning you could potentially see more than half the star's surface at once, as light from the far side curves around to reach you. The star would appear larger than its actual size because gravity acts as a lens. One of the most fascinating aspects of neutron stars is their role as cosmic timekeepers. Because they're so massive and compact, their rotation is incredibly stable. Millisecond pulsars, neutron stars that spin hundreds of times per second, are among the most stable natural clocks in the universe, rivaling or exceeding the precision of atomic clocks on Earth. Astronomers use this precision for some remarkable applications. Arrays of millisecond pulsars scattered across the galaxy are being used to detect gravitational waves through a technique called pulsar timing. When a gravitational wave passes through the galaxy, it subtly changes the distances between Earth and these pulsars, causing tiny timing variations in when their pulses arrive. By monitoring dozens of pulsars simultaneously over many years, astronomers hope to detect gravitational waves from supermassive black hole mergers in distant galaxies. Let me address a common misconception. Many people think neutron stars are made of neutronium, some exotic form of matter. While the term neutronium is sometimes used colloquially, it's not a specific substance. A neutron star is made primarily of neutrons, yes, but it's more accurate to think of it as a giant atomic nucleus, held together by gravity rather than the strong nuclear force. In a sense, a neutron star is one enormous city-sized nucleus. Another misconception is that all neutron stars are pulsars. Actually, pulsars are just neutron stars whose magnetic axis is misaligned with their rotation axis, causing the lighthouse effect. If the beams don't sweep across Earth, we don't see pulses. It's estimated that only about 10% of neutron stars are oriented such that we detect them as pulsars. The other 90% are out there, spinning away, but we can't easily detect them unless they're in binary systems or we detect them through other means. Neutron stars and binary systems provide some of the universe's most extreme laboratories. When a neutron star orbits a normal star closely enough, it can pull material from its companion, creating an accretion disk of stolen matter spiraling onto the neutron star. This material, accelerated to relativistic speeds by the intense gravity and heated to millions of degrees, produces intense X-ray emission. These X-ray binary systems are some of the brightest X-ray sources in the sky. In some cases, the accreting material builds up on the neutron star's surface until it undergoes thermonuclear fusion in an explosive burst, creating what's called an X-ray burster. These bursts can briefly outshine the entire galaxy in X-rays. It's like a cosmic bomb going off on the surface of the neutron star, releasing the energy of 1,000 supernovae in a matter of seconds, though concentrated in a tiny area. One particularly exotic phenomenon is the recycled pulsar. When a neutron star in a binary system accretes matter from its companion, the infalling material carries angular momentum, spinning up the neutron star like a cosmic merry-go-round being pushed. Over millions of years, this can accelerate the neutron star to incredible rotation rates. Some recycled millisecond pulsars spin over 700 times per second, having been spun up by this accretion process. These old neutron stars, born in supernovae billions of years ago, have been given a second life by their companion stars. Can you imagine what it means for an object that massive to change its rotation rate? The angular momentum involved is staggering. Spinning up a neutron star is like trying to change the rotation rate of a planet. The fact that accreted matter can achieve this demonstrates the incredible amounts of material and energy involved in these systems. Here's something to ponder. Neutron stars might be the only places in the universe where we can observe matter in forms that briefly existed in the first microseconds after the Big Bang. In the ultra-hot, ultra-dense conditions of the early universe, matter likely existed in forms similar to what we find in neutron star cores. By studying neutron stars, we're probing physics that hasn't existed anywhere else in the universe for nearly 14 billion years. The extreme physics of neutron stars continues to surprise us. In 2017, the detection of gravitational waves from two neutron stars merging, an event we'll explore more deeply later, provided the first direct evidence that neutron star collisions are a major source of heavy elements like gold and platinum. The merger also produced a kilonova, a new type of explosion powered by radioactive decay of heavy elements synthesized in the collision. But there's a limit to how much mass a neutron star can contain. Beyond about 2 to 3 solar masses, depending on the exact equation of state of nuclear matter, even neutron degeneracy pressure fails. When that limit is exceeded, nothing in physics can stop the collapse. No known force can prevent what comes next. The stellar remnant crosses a threshold beyond which the concept of a physical surface becomes meaningless, where gravity becomes so intense that not even light can escape, where space-time itself curves back on itself. This is where neutron stars give way to something even more extreme, even more mysterious, the ultimate endpoint of stellar death for the most massive stars. There exists a boundary in space beyond which nothing, absolutely nothing can return. Not light, not matter, not information itself. Cross this invisible line, called the event horizon, and your fate is sealed. You will be pulled inexorably toward a point of infinite density where the laws of physics as we understand them break down completely. Time itself behaves so strangely near this boundary that from the outside perspective, you would appear to freeze at the edge, suspended forever at the moment of crossing, while from your perspective, you'd fall through in finite time toward your destruction. This is a black hole, the universe's ultimate prison, formed when the most massive stars die and collapse beyond even neutron star density. And here's what kept physicists awake for decades. We weren't even sure they could exist until we actually found one. If you're captivated by these cosmic mysteries at the edge of known physics, please show your support by liking this video and subscribing. Your engagement truly helps us continue exploring the universe's deepest enigmas. The theoretical possibility of black holes has a surprisingly long history. In 1783, more than a century before Einstein's theory of relativity, an English clergyman and natural philosopher named John Michell wondered, what if a star was so massive that its escape velocity exceeded the speed of light? Even using Newtonian physics, he realized such an object would be invisible, trapping its own light. He called these hypothetical objects dark stars. But black holes as we understand them today required Einstein's general theory of relativity, published in 1915. Einstein's revolutionary insight was that gravity isn't a force pulling objects together, but rather a curvature of space-time itself. Massive objects bend the fabric of space and time around them, and other objects follow the curved paths through this warped space-time. Just months after Einstein published his field equations, a German physicist serving on the Russian front during World War I, Karl Schwarzschild, found an exact solution to Einstein's equations describing the spacetime around a spherically symmetric mass. Schwarzschild's solution contained something strange, a mathematical singularity at a specific radius, now called the Schwarzschild radius, where the equations seemed to break down. For an object with the Sun's mass, this radius was about 3 kilometers. For Earth's mass, it was about 9 millimeters. Schwarzschild died just months later from a disease contracted at the front, never knowing that his solution described what would become the most studied objects in theoretical physics. For decades, physicists debated whether the Schwarzschild radius represented a real physical phenomenon or just a mathematical artifact. Even Einstein was skeptical that such extreme objects could actually form in nature. The term black hole wasn't coined until 1967 by physicist John Wheeler in a stroke of linguistic genius that gave these objects a name that perfectly captured their mysterious and somewhat terrifying nature. Before that, they were called collapsed stars or frozen stars, names that completely failed to capture the public imagination the way black hole did. But the real revolution came when astronomers figured out how to detect these invisible objects. After all, if black holes emit no light, how do you find them? The answer: look for their gravitational effects on nearby matter. In 1964, a rocket-borne X-ray detector discovered an intense X-ray source in the constellation Cygnus, designated Cygnus X1. When optical telescopes examined that region, they found a blue supergiant star designated HDE 226868. Detailed observations showed this star was orbiting something invisible, something massive, every 5.6 days. By measuring the orbital period and the star's velocity, astronomers could calculate the mass of the invisible companion. It was at least 6 solar masses, far too massive to be a neutron star. The intense X-rays were coming from an accretion disk of material stolen from the supergiant, heated to millions of degrees as it spiraled toward the compact object. The conclusion was inescapable. Cygnus X1 was a black hole. This discovery was so controversial that Stephen Hawking, who had built much of his early career on black hole physics, made a bet with fellow physicist Kip Thorne in 1975. Hawking bet that Cygnus X1 was not a black hole. This seems counterintuitive, but Hawking explained his reasoning. If black holes didn't exist, then his work on them was at least mathematically interesting. But if they did exist, and he was wrong about Cygnus X1, at least he'd have the consolation of winning the bet. It was, as he put it, an insurance policy. By 1990, the evidence had become overwhelming. Hawking conceded the bet, famously breaking into Thorne's office while he was away and signing the concession in Thorne's bet book. Cygnus X1 was indeed a black hole, and we now know of thousands more. But what exactly is a black hole? Let me describe the structure of these objects, because they're far more complex than the popular image of a cosmic drain suggests. At the center of a black hole is the singularity, a point of infinite density where all the black hole's mass is concentrated. I say point, but we need to be careful. The singularity isn't a place in the normal sense. It's more like a moment in time, an inevitable future for anything that crosses the event horizon. Our physics breaks down at the singularity, giving us results that include infinite density and infinite curvature of space-time, which almost certainly means our theories are incomplete rather than infinity being physically real. Surrounding the singularity is the event horizon, the boundary of no return. The radius of this boundary is the Schwarzschild radius, directly proportional to the black hole's mass. For a black hole with 10 times the sun's mass, the event horizon has a radius of about 30 kilometers. For a supermassive black hole with 1 billion solar masses, like those found at the centers of large galaxies, the event horizon can be larger than our entire solar system. Here's something that surprises many people. The event horizon isn't a physical surface. It's not made of anything. It's just a mathematical boundary in space-time, the point beyond which escape becomes impossible. If you were falling toward a black hole, you wouldn't feel anything special as you cross the event horizon. There's no wall, no barrier, no sudden sensation. You'd simply pass through, and only later would you realize you could never return. For rotating black holes, which is probably all black holes in reality, since stars rotate and angular momentum is conserved during collapse, the structure becomes more complex. There's an outer boundary called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, you cannot remain stationary. You must rotate with the black hole, even if you fire rockets trying to stay still. The rotation literally drags space-time along with it. At the inner edge of the ergosphere is another event horizon, the outer event horizon of the rotating black hole. And in theory, there's an inner event horizon as well, though we're not sure if this mathematical feature corresponds to physical reality. The singularity in a rotating black hole isn't a point, but a ring, called a ring singularity, around which you might theoretically be able to orbit without being destroyed, though this is purely theoretical and probably not possible in practice. The most bizarre aspect of black holes is what they do to time. According to general relativity, time flows more slowly in stronger gravitational fields. Near a black hole, this effect becomes extreme. If you were watching someone fall toward a black hole, you'd see them move more and more slowly as they approach the event horizon. Their clock would appear to tick slower and slower. Light from them would be redshifted, stretched to longer and longer wavelengths. As they reach the event horizon, from your perspective, they would appear to freeze, taking infinite time to cross the boundary. But from the falling person's perspective, everything would seem normal. Their clock would tick normally. They'd cross the event horizon in finite time, perhaps just seconds or minutes, depending on the black hole's mass. This creates a profound paradox. From outside, the person never quite reaches the event horizon. From inside, they've already crossed it and are doomed. Both perspectives are equally valid in relativity. This leads to what's called the black hole information paradox, one of the deepest problems in theoretical physics. When something falls into a black hole, what happens to the information it contains? According to general relativity, the information crosses the event horizon and is lost forever, eventually destroyed at the singularity. But according to quantum mechanics, information cannot be destroyed. It must be preserved in some form. Stephen Hawking spent decades working on this problem. In 1974, he discovered that black holes aren't entirely black. Quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This radiation is incredibly faint and would be undetectable for any black hole we could actually observe, but it's theoretically significant. Hawking radiation means black holes slowly evaporate, losing mass over time. For a stellar mass black hole, the time to evaporate via Hawking radiation is about 10 by 67 years, an unimaginably long time. For a supermassive black hole, it's even longer. But eventually, given enough time, all black holes will evaporate completely. The question is, what happens to the information about everything that ever fell in? Does it escape somehow in the Hawking radiation? Or is it destroyed, violating quantum mechanics? Hawking originally believed information was destroyed, but after decades of debate, he reversed his position in 2004, conceding another famous bet to John Preskill. Current thinking, though far from settled, suggests information might be preserved in subtle correlations in the Hawking radiation. But exactly how this works remains one of physics' great unsolved problems. Let me address a common misconception that drives physicists crazy. Black holes do not suck. They don't have some special suction force. The gravity of a black hole at a given distance is exactly the same as the gravity of any other object with the same mass. If you replace the sun with a black hole of equal mass, Earth's orbit wouldn't change at all. We'd freeze in the darkness, but we wouldn't be sucked into the black hole. What makes black holes special is that all their mass is concentrated into such a tiny volume. This means you can get extremely close to all that mass, where the gravitational field becomes incredibly strong. If the sun became a black hole, you could approach within 3 kilometers of all its mass, where the gravity would be extreme. But the sun isn't massive enough to become a black hole. It'll end as a white dwarf. Only the cores of massive stars, those with more than about 20-25 solar masses originally, will collapse into black holes. Another misconception is that crossing the event horizon means instant death. For a supermassive black hole, with its enormous event horizon, you could cross the boundary and survive for a considerable time before tidal forces became lethal. You'd be doomed, unable to escape, but not immediately destroyed. For a stellar mass black hole, the tidal forces are much stronger near the event horizon, and you'd likely be torn apart before or shortly after crossing. The tidal forces, called spaghettification, in a term that's equal parts descriptive and horrifying, occur because black holes create extreme gravitational gradients. If you fell feet first toward a black hole, the gravity pulling your feet would be significantly stronger than the gravity pulling your head. This difference stretches you vertically while compressing you horizontally, elongating you like spaghetti. For a stellar mass black hole, this would kill you long before you reach the event horizon. For a supermassive black hole, you might survive spaghettification long enough to cross the horizon before being ultimately destroyed near the singularity. But perhaps the most significant breakthrough in black hole astronomy came in 2019, when the Event Horizon Telescope collaboration released the first actual image of a black hole. This wasn't a black hole in our galaxy, but the supermassive black hole at the center of the galaxy, M87, some 55 million light-years away. The image showed a bright ring of light surrounding a dark circular region, exactly as general relativity predicted. The ring is created by the photon sphere, a region outside the event horizon where light orbits the black hole. Some of this light escapes toward us, creating the bright ring. The dark region in the center, larger than the event horizon itself, is called the black hole's shadow. It's the region from which no light can reach us, including the event horizon and the photon sphere on the far side of the black hole. The M87 black hole has a mass of about 6.5 billion suns. The event horizon has a diameter of about 38 billion kilometers, large enough that light takes more than a day to cross it. The bright ring we see is created by an accretion disk of superheated plasma orbiting at significant fractions of light speed, heated to billions of degrees by friction and magnetic fields as it spirals inward. Creating this image required linking radio telescopes across the entire Earth, creating a virtual telescope the size of our planet. The data amounted to 5 petabytes, enough to fill half a ton of hard drives. That data had to be physically flown to correlation facilities because it was too much to transmit over the internet. The imaging process involved sophisticated algorithms developed over years, including crucial contributions by computer scientist Katie Booman. This image did more than just show us a black hole for the first time. It confirmed that Einstein's general relativity still holds in these extreme conditions, a century after he formulated it. The size, shape, and properties of the shadow match theoretical predictions with remarkable precision. In 2022, the Event Horizon Telescope collaboration released a second image, this one of Sagittarius A(As), the supermassive black hole at the center of our own Milky Way galaxy. With a mass of about 4 million suns, it's much smaller than M87's black hole, but much closer, only 26,000 light-years away. Imaging it was actually more challenging because matter orbits it much faster, creating a rapidly changing structure that blurs during observations. Have you ever wondered what the ultimate fate of black holes is? Through Hawking radiation, all black holes will eventually evaporate, but the timescales are almost incomprehensible. A solar mass black hole will take about 10 dwarfs 67 years to evaporate. For perspective, the current age of the universe is only 1. 38 x 10 more than 10 years. By the time stellar mass black holes begin to evaporate significantly, the universe will be unimaginably old and cold, with all stars long dead, all matter decayed. Supermassive black holes will last even longer. The largest black holes might take 10 to 100 years or more to evaporate completely. These timescales dwarf the current age of the universe by a factor so large it's almost meaningless. But eventually, quantum mechanics insists. Even black holes must fade away, returning their mass energy to the cosmos in the form of radiation. There's also the fascinating question of what you'd see if you fell into a black hole. As you cross the event horizon, looking back toward the universe you left, you'd see time-lapsed images of everything that happens outside, in principle watching the rest of cosmic history unfold and fast forward. Looking ahead toward the singularity, you'd see highly distorted, blue-shifted images of matter and light falling in with you. The experience would be utterly alien, with the normal geometry of space completely warped. Some physicists have speculated about traversable wormholes, hypothetical structures that might connect 2 black holes or 2 different regions of space-time. If such structures exist, they might theoretically allow faster-than-light travel, not by exceeding light speed locally, but by taking shortcuts through space-time. However, all known solutions that would create traversable wormholes require exotic forms of matter with negative energy density, and we have no evidence such matter can exist in the quantities required. Wormholes remain firmly in the realm of speculation. Black holes represent the absolute boundary of stellar death, the ultimate endpoint for the most massive stars. They're laboratories where quantum mechanics and gravity collide, revealing the limits of our current physics. They challenge our understanding of space, time, matter, information, and causality itself. They're proof that reality can be stranger than anything science fiction writers imagined. But detecting black holes, measuring their properties, imaging their shadows, these achievements require decades of technological development and theoretical work. The tools and techniques astronomers use today to study stellar remnants, from white dwarfs to neutron stars to black holes, represent some of humanity's greatest intellectual and engineering achievements. Understanding how we observe these objects, the incredible technology and methods involved, reveals yet another layer to the story of stellar death. On September 14, 2015, at 5:51 a.m. Eastern Time, two detectors in Louisiana and Washington State, separated by 3,000 kilometers, detected a signal that lasted just 1/5 of a second. This signal, a tiny distortion in space-time itself, had traveled for 1.3 billion years across the universe. It was created when two black holes, each roughly 30 times the mass of our Sun, spiraled together and merged, releasing more energy in that fraction of a second than all the stars in the observable universe combined. For the first time in human history, we had heard the universe, detecting gravitational waves and opening an entirely new way of observing cosmic catastrophes. This wasn't light, radio waves, or any form of electromagnetic radiation. This was space-time itself, rippling like the surface of a pond, carrying information about events that no telescope could ever see. If you're amazed by how far our observational capabilities have come, please take a moment to like this video and subscribe to the channel. Your support helps us share these incredible stories of human ingenuity and cosmic discovery. The detection of gravitational waves represents one of the most remarkable technological achievements in scientific history. And the story of how we got there spans a century of theoretical prediction, experimental setbacks, and persistent effort. Einstein predicted gravitational waves in 1916, just 1 year after publishing his general theory of relativity. His equation suggested that accelerating masses should create ripples in space-time that propagate at the speed of light. But Einstein himself doubted we'd ever detect them. The effect is incredibly weak. Even the merger of two black holes, occurring relatively nearby in cosmic terms, creates a distortion in space-time at Earth of about 1 part in 10⁻²⁻21. That means the distance between the two LIGO detectors, 3,000 kilometers apart, changed by less than 1,000th the diameter of a proton when the gravitational wave passed through. To put that in perspective, imagine trying to measure the distance to the nearest star, Alpha Centauri, forcing 37 light-years away, to an accuracy smaller than the width of a human hair. That's the level of precision LIGO achieved. The detectors use laser interferometry, splitting a laser beam and sending the two halves down perpendicular 4-kilometer-long tunnels, then recombining them. When a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction, causing a tiny change in the relative path lengths the laser beams travel. This creates an interference pattern that reveals the wave's passage. Building detectors capable of such precision required overcoming countless sources of noise. Seismic vibrations from traffic, ocean waves, even atmospheric pressure changes can create disturbances far larger than a gravitational wave signal. The detectors had to be isolated from vibration using sophisticated suspension systems. Laser light itself creates quantum noise that had to be minimized. Thermal noise from molecular motion in the mirrors had to be reduced by using mirrors made of the purest fused silica and sapphire, polished to near atomic smoothness. The LIGO project began in the 1990s, with initial funding coming after decades of advocacy by physicists like Kip Thorne, Rainer Weiss, and Ronald Drever. The first-generation detectors ran from 2002 to 2010 and detected nothing, exactly as expected. They weren't quite sensitive enough. Advanced LIGO, with dramatically improved sensitivity, came online in September 2015. The fact that it detected a black hole merger just days after beginning operation was extraordinary luck, though it also reflected the fact that these mergers happen more frequently than some models had predicted. The 2015 detection, designated GW10914, revolutionized astronomy overnight. the gravitational wave signal rose in frequency and amplitude, a chirp lasting just 2 seconds as the two black holes spiraled together at ever-increasing speeds, reaching 250 orbits per second in their final moments. From this brief signal, physicists extracted incredible information. The masses of the two black holes, their spins, their distance from Earth, and the mass and spin of the final merged black hole. About 3 solar masses worth of mass energy was converted directly into gravitational radiation in that final fifth of a second, confirming Einstein's famous equation E = mc2 in the most violent way possible. Rainer Weiss, Kip Thorne, and Barry Barish shared the 2017 Nobel Prize in Physics for this achievement, one of the fastest transitions from detection to Nobel Prize in modern physics, reflecting the discovery's profound importance. But the revolution didn't stop with black hole mergers. On August 17, 2017, LIGO detected a different type of signal, longer and from a less massive system. Within seconds, astronomers around the world received alerts. This wasn't just 2 black holes merging. This signal suggested 2 neutron stars spiraling together. And unlike black hole mergers, which emit only gravitational waves, neutron star mergers should produce electromagnetic radiation as well. Within 2 seconds of the gravitational wave detection, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. This was the smoking gun, confirming that the gravitational waves came from a neutron star collision. Then began the most intensive astronomical observation campaign in history. Telescopes across the electromagnetic spectrum, from radio to gamma rays, on the ground and in space, turned toward the source location in the galaxy NGC 4993, about 130 million light-years away. What they saw was extraordinary. A kilonova, a new type of explosion powered by the radioactive decay of heavy elements synthesized in the merger. The collision had created a fireball of neutron-rich matter. And in this extreme environment, rapid neutron capture, the R process we discussed earlier, forged enormous quantities of gold, platinum, uranium, and other heavy elements. Spectroscopic analysis confirmed the presence of these newly synthesized elements. We had finally witnessed the cosmic forges that create most of the universe's gold and platinum. This single event, observed in both gravitational waves and light, marked the beginning of multi-messenger astronomy, the practice of observing cosmic events using multiple types of signals: gravitational waves, electromagnetic radiation, neutrinos, potentially even cosmic rays. Each messenger carries different information, and by combining them, we get a far more complete picture than any single type of observation could provide. But gravitational wave detectors aren't the only revolutionary tools transforming our ability to study stellar deaths. The Event Horizon. Telescope's imaging of black holes represents another technological tour de force. The EHT isn't a single telescope, but a network of radio telescopes spread across the globe, from Hawaii to Chile to Antarctica to Europe. By combining their signals using a technique called Very Long Baseline Interferometry, or VLBI, they create a virtual telescope with an effective diameter equal to the distance between the telescopes, in this case, nearly the size of Earth. Here's why that matters. The resolution of any telescope, its ability to see fine detail, is limited by diffraction. Roughly speaking, the smallest angle you can resolve is proportional to the wavelength of light you're observing divided by the diameter of your telescope. To see the shadow of a black hole, you need to resolve angles of about 20 microarc seconds, roughly equivalent to seeing a grapefruit on the surface of the moon from Earth. No single telescope can achieve this resolution at the radio wavelengths needed to peer through the gas surrounding supermassive black holes. But by linking telescopes across the Earth and combining their signals, the EHT achieves this seemingly impossible resolution. The data from each telescope is precisely time-stamped using atomic clocks. Then the signals are combined computationally to create an image. The computational challenge is immense. The EHT observes at such high data rates that the information cannot be transmitted over the internet. Instead, the data is recorded on hard drives, which are physically shipped to correlation facilities at MIT's Haystack Observatory and the Max Planck Institute for Radio Astronomy in Germany. The data from the Antarctic telescope has to wait months until the Antarctic winter ends and planes can fly to the South Pole Station. Creating an image from this data requires sophisticated algorithms that account for the Earth's rotation, atmospheric effects, and the sparse coverage of the telescope network. The imaging algorithms were developed over years, with crucial contributions from computer scientist Katie Booman and many others. Multiple independent imaging approaches were used, and the fact that they all produced consistent results gave confidence that the final image was real and not an artifact of the processing. The M87 black hole image released in 2019 represented data from observations made in April 2017. 2 years from observation to publication might seem slow, but it reflects the immense complexity of processing and validating the data. When the image was finally released, it made headlines worldwide, becoming one of the most iconic scientific images of the 21st century. Space-based telescopes have also revolutionized our study of stellar remnants. The Chandra X-ray Observatory, launched in 1999, has given us unprecedented views of supernova remnants, neutron stars, and black hole accretion disks. X-rays are emitted by matter heated to millions of degrees, exactly the conditions found in these extreme environments. Chandra's observations of supernova remnants like Cassiopeia A have revealed the distribution of elements ejected in the explosion, effectively performing stellar autopsies. We can see where the iron synthesized in the core ended up, where the silicon and sulfur from intermediate layers were thrown, mapping out the three-dimensional structure of the explosion. Chandra has also imaged the jets from black holes, narrow beams of particles accelerated to nearly light speed and shot thousands of light years into space. The Hubble Space Telescope, operating primarily in visible and near ultraviolet light, has monitored supernova remnants over decades, watching them expand and evolve. Time-lapse sequences of images from Hubble have revealed the complex dynamics of these explosions, showing shock waves plowing through surrounding gas, knots of material moving at different speeds, and light echoes reflecting off intervening dust clouds. The James Webb Space Telescope, launched in 2021, observes primarily in infrared light, which penetrates dust that blocks visible light. This makes JWST ideal for studying dusty supernova remnants and the environments where stars form and die. Early JWST observations have already revealed unprecedented detail in structures like the Crab Nebula's complex filaments and the shells of material around dying stars. Ground-based telescopes continue to play crucial roles as well. The Very Large Telescope in Chile, with its 4 8.2-meter mirrors, can study stellar remnants in exquisite detail. Adaptive optics systems, which use deformable mirrors to compensate for atmospheric blurring in real time, have dramatically improved the resolution of ground-based telescopes, allowing them to rival space telescopes for many observations. One of the most exciting developments is the network of supernova early warning systems. When a nearby star goes supernova, the first signal we'll receive is neutrinos, arriving hours before the light from the explosion. Neutrino detectors like Super Cameo Kande in Japan, Ice Cube at the South Pole, and others are constantly monitoring for the characteristic burst of neutrinos that would signal a core collapse supernova within our galaxy or nearby galaxies. The Supernova Early Warning System, or SNOOS, is a network that links multiple neutrino detectors. If two or more detectors see a neutrino burst within a 10-second window, the system automatically alerts astronomers worldwide. This would give telescopes precious hours to orient themselves toward the supernova before the light arrives, potentially capturing the first moments of the explosion, the shock wave breaking through the star's surface. We haven't had a nearby supernova since 1987, before most modern instruments existed. When the next one occurs, we'll have an armada of telescopes ready to observe it across the electromagnetic spectrum, plus neutrino detectors and gravitational wave detectors all coordinating their observations. It will be the most comprehensively observed astronomical event in history. Citizen scientists also contribute to supernova discovery. Automated surveys like the Zwicky Transient Facility scan the entire visible sky every few nights, looking for anything that changed: new stars, supernovae, asteroids, variable stars. The data is processed by computers, but human volunteers help classify the candidates, distinguishing real supernovae from artifacts and other transient phenomena. Amateur astronomers with modest telescopes have discovered supernovae that professionals then follow up with larger instruments. This democratization of astronomy is remarkable. 100 years ago, astronomy was the province of a few dozen professional astronomers with access to the world's largest telescopes. Today, amateurs with telescopes purchased for a few $1,000s contribute meaningful observations, and anyone with internet access can participate in citizen science projects analyzing real astronomical data. Let me address a common misconception. Many people think modern astronomy is all automated, computers scanning the sky while astronomers sit back. While automation has certainly increased, human insight remains crucial. Automated systems can detect anomalies, but understanding what you're seeing, distinguishing between different types of transient events, recognizing when something genuinely new and unexpected appears, all of this requires a human expertise and intuition. The 2017 neutron star merger is a perfect example. Automated systems detected the gravitational waves and gamma rays, but it took experienced astronomers to quickly coordinate observations across dozens of telescopes to decide which instruments to use, which wavelengths to observe, how to schedule precious telescope time. The scientific insights from that event came from human analysis and interpretation, not just from automated data processing. Another misconception is that we understand everything we observe. In reality, stellar remnants continue to surprise us. Magnetar flares exceed theoretical predictions for how much energy magnetic field restructuring can release. Some neutron stars appear to have glitches, where their rotation suddenly speeds up, suggesting complex physics in their interiors. The jet mechanisms in black holes remain incompletely understood. Every new observation potentially reveals something unexpected. What might future instruments reveal? Plans are underway for even more sensitive gravitational wave detectors. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will detect gravitational waves from space, free from seismic noise. LISA will be sensitive to lower frequencies than ground-based detectors, allowing it to observe supermassive black hole mergers across cosmic time. Future extremely large telescopes, with mirrors 30 to 39 meters in diameter, will study stellar remnants with unprecedented detail. The Square Kilometer Array, A radio telescope network spread across continents with a combined collecting area of 1 square kilometer will revolutionize radio astronomy, potentially detecting thousands of new pulsars and studying neutron star populations throughout the galaxy. Multi-messenger astronomy will become increasingly sophisticated as more detectors come online and coordination improves. Future supernova observations might combine gravitational waves from the core collapse, neutrinos from the neutron star formation, electromagnetic radiation across all wavelengths, and perhaps even neutrinos from subsequent accretion onto the neutron star or black hole. Each messenger would provide unique information, together painting a complete picture of one of the universe's most violent events. Have you ever considered what it means that we can study events so distant in space and time? When we observe a supernova in a galaxy 100 million light years away, we're seeing an event that occurred 100 million years ago, when dinosaurs still roamed Earth. The light has been traveling through space for longer than our species has existed, carrying information about a stellar death that happened in an epoch when Earth's story was completely different. We're not just exploring space, we're exploring time itself, archaeology on a cosmic scale. All these observations, all this technology, all this accumulated knowledge about stellar death point toward profound questions about the future. We've traced the deaths of stars, from the gentle fading of white dwarfs to the spectacular explosions of supernovae, to the formation of neutron stars and black holes. But what happens on even longer time scales? What is the ultimate fate of all these stellar remnants as the universe ages? Where does this all lead as we look not millions or billions, but trillions and quadrillions of years into the future? In the year 100 trillion CE, approximately 860,000 years from now, the last star in the universe will exhaust its fuel and fade into darkness. After that moment, no new stars will ever form. The era of starlight, the epoch in cosmic history, when galaxies gleamed with billions of suns, when stellar births and deaths enriched the universe with heavy elements, when life could evolve on planets warmed by stellar fusion, will be over. The universe will enter an age of darkness, cold, and decay that will last not for billions or trillions of years, but for timescales so vast that the entire age of stars, from the first generation after the Big Bang until the last star dies, represents merely the first fleeting moments of cosmic history. This is not science fiction. This is cosmology's best understanding of the deep future, a future where stellar death isn't an event, but a permanent state. If contemplating the universe's ultimate destiny intrigues you, please show your support with a like and subscription. These explorations of cosmic endings and deep time are some of the most profound journeys we can take together. The far future of the universe has been seriously studied by cosmologists for decades, with landmark papers by Freeman Dyson in 1979 and Fred Adams and Gregory Laughlin in 1997, laying out detailed timelines of cosmic evolution over unimaginable timescales. What they described is both melancholic and strangely beautiful, a universe gradually winding down, transitioning through distinct eras as different processes dominate. We currently live in what cosmologists call the stelliferous era, the age of stars, which began about 100 million years after the Big Bang when the first stars formed, and will continue for approximately 100 trillion years total. We're experiencing this era at just 13.8 billion years, meaning we're witnessing the universe when it's only about 0.01% through its star-forming phase. In cosmic terms, the universe is extraordinarily young. The party is just getting started, but star formation is already declining. The universe's rate of star formation peaked about 10 billion years ago and has been decreasing ever since. The reason is straightforward. Star formation requires gas, primarily hydrogen, and that gas is gradually being locked up in stars, stellar remnants, and planets. Additionally, the universe's expansion is spreading galaxies apart, making interactions and mergers less common. These interactions trigger intense bursts of star formation by compressing gas clouds. Fewer interactions mean less star formation. Over the next few trillion years, the rate of star formation will continue to decline. Large, massive stars, those that burn hot and die young, will become increasingly rare. The last massive stars capable of exploding as supernovae will likely die within the next 100 billion years or so. After that, the only stars forming will be small, cool red dwarfs, the smallest stars capable of sustaining hydrogen fusion. Red dwarfs are the universe's misers, burning their fuel so slowly that the smallest ones could theoretically shine for 10 trillion years or more, far longer than the current age of the universe. Because they're so efficient and so numerous, already comprising about 75% of all stars, red dwarfs will dominate the final stages of the stelliferous era. The last stars in the universe will almost certainly be red dwarfs, tiny embers barely massive enough to sustain fusion, sipping their hydrogen fuel over time scales that dwarf all of recorded history by factors of millions. Imagine the galaxy in the year 10 trillion CE. The Milky Way and Andromeda will have long since merged into a single elliptical galaxy. Most of the bright, massive stars we see in our current night sky will be gone. Their lives ended billions of years ago. The galaxy will be dimly lit by the feeble glow of countless red dwarfs and the stored heat of cooling white dwarfs. Star formation will be almost completely ceased. Planetary systems will be ancient beyond comprehension. Their planets geologically dead. Their atmospheres long since frozen or lost to space. And what of stellar remnants during this epoch? White dwarfs, already numerous today, will vastly outnumber active stars. There will be billions upon billions of them in every galaxy, slowly cooling, gradually fading from white to red to brown to black. But even after 10 trillion years, they'll still be warm, still radiating residual heat. The first black dwarfs, completely cooled white dwarfs at the temperature of the cosmic background, won't appear until perhaps 100 trillion years, possibly much longer. Neutron stars will still exist, though most will have spun down, no longer emitting detectable radio pulses. They'll be dark, invisible, except through their gravitational effects. Black holes will be essentially unchanged, slowly growing through the occasional accretion of wandering matter, but hardly different from their formation. Around the 100 trillion year mark, the last red dwarf will exhaust its hydrogen fuel. There will be no more fusion anywhere in the universe. The stelliferous era will end, and the degenerate era will begin, an epoch dominated not by active stars, but by stellar remnants, white dwarfs, neutron stars, and black holes. The degenerate era will last from about 1014 years to perhaps 1040 years, depending on the physics of proton decay, which remains uncertain. During this era, the primary sources of energy in the universe will be the residual heat of white dwarfs, the occasional collision of stellar remnants, and possibly the decay of matter itself. Galaxies during the degenerate era will be invisible in any wavelength we currently observe. No stars shine. White dwarfs are too cool to emit visible light. The galaxy would be dark, a collection of black and brown dwarfs, neutron stars, and black holes, detectable only through gravitational effects. If intelligent beings somehow existed during this era, they would look out and see nothing but darkness, perhaps occasionally punctuated by the faint glow of a white dwarf collision or the brief flash of matter falling into a black hole. But Dynamics continue even in this darkness. Stellar remnants in galaxies orbit the galactic center, and occasionally they pass close to each other. These gravitational encounters can eject objects from the galaxy entirely, flinging them into intergalactic space, or they can cause orbits to decay, sending objects spiraling toward the galactic center. Over timescales of 1019 to 10 to 20 years, this process, called gravitational relaxation, will gradually disperse galaxies. Most stellar remnants will be ejected into the void, while a small fraction will fall into the supermassive black hole at the galactic center, causing it to grow. Meanwhile, stellar remnants that remain in proximity might occasionally collide. White dwarf collisions, though rare on human timescales, become inevitable given enough time. When two white dwarfs collide, if their combined mass exceeds the Chandrasekhar limit, they explode as a Type Ia supernova, a final brilliant flash in the darkness, briefly illuminating the dead galaxy before fading back to black. Neutron star collisions will continue to occur as well, creating bursts of gravitational waves that propagate through the empty cosmos. These collisions will synthesize the last heavy elements that will ever be created, gold and platinum forming in a universe that has no use for them, where no planets or life forms will ever incorporate them. Now, here's where physics becomes deeply uncertain. The standard model of particle physics predicts that protons are stable, lasting forever. But some extensions of the standard model, particularly grand unified theories, predict that protons should slowly decay with a half-life somewhere between 1032 and 1040 years. If proton decay occurs, it will dominate the next era of cosmic history. In the black hole era, beginning around 10 to 40 years if protons decay, or perhaps much later if they don't, the remaining stellar remnants will slowly evaporate. White dwarfs, neutron stars, even planets and asteroids, all are made of protons and neutrons. If these particles decay, solid matter will gradually convert into radiation, electrons, positrons, and neutrinos. A white dwarf would slowly fade as its constituent particles decay one by one, releasing energy in the process. Over timescales of 10 to 40 years, all matter would decay, leaving only black holes, electrons, positrons, neutrinos, and photons. But black holes themselves are not eternal. Stephen Hawking's discovery of black hole evaporation means that even these ultimate stellar endpoints will eventually disappear. Through quantum effects near the event horizon, black holes emit Hawking radiation, very slowly losing mass and energy. The timescale for black hole evaporation scales with the cube of the mass. A stellar mass black hole, say 10 solar masses, will take approximately 10 to 67 years to evaporate completely. A supermassive black hole like the one at the center of our galaxy, with about 4 million solar masses, will take roughly 10 to 87 years. The most massive black holes, with tens of billions of solar masses, might take 100 years or longer. Think about these timescales for a moment. 10 more than 67 years is 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000. 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000 years. Written out, it's incomprehensible. The current age of the universe, 13.8 billion years, is utterly negligible compared to this. It's like comparing a single second to a trillion years. No, even that comparison vastly understates the difference. During the black hole era, the universe will be almost completely empty. Particles of radiation will be separated by light years, space years, distances so vast that encountering another particle would be extraordinarily rare. Black holes will be the only significant concentrations of mass energy, and they'll be separated by distances greater than the currently observable universe. The universe will be cold, approaching absolute zero, dark, and essentially devoid of structure. As black holes evaporate, they'll become hotter. A black hole's Hawking temperature is inversely proportional to its mass. Small black holes are hotter than large ones. As a black hole evaporates and loses mass, it heats up, radiating faster, which causes it to lose mass even more quickly in a runaway process. In its final moments, a black hole will evaporate explosively, releasing its remaining mass energy in a burst of high-energy particles and radiation. This final flash will be the last significant energy release in that region of space, perhaps the final event of any consequence in that particular cosmic neighborhood. After all black holes have evaporated, around 10 to 100 years or later, the universe will enter what's called the dark era. At this point, the universe will contain only radiation, primarily photons from black hole evaporation, along with electrons, positrons, neutrinos, and perhaps some exotic particles. These particles will be spread so thinly that the average distance between any two particles will be measured in thousands, millions, or billions of light years. The temperature of the universe will be infinitesimally close to absolute zero, limited only by the expansion of space itself, which will have stretched the wavelengths of all remaining photons to absurd lengths. The cosmic background radiation, currently at about 2.7 Kelvin, will have cooled to something like 10⁻30 Kelvin or less. At such temperatures, essentially no physical processes can occur. The universe will have reached a state of maximum entropy, the heat death. This is thermodynamics' ultimate prediction. All organized structures decay, all energy gradients dissipate, all temperature differences even out. The heat death doesn't mean the universe gets hot. It means the universe reaches thermal equilibrium at a temperature only infinitesimally above absolute zero. No heat can flow because there are no temperature differences. No work can be extracted because there are no energy gradients. Nothing can happen because there's no available energy to drive processes. Let me address a common misconception about the heat death. Some people imagine it as a dramatic end, an explosive finale. It's the opposite. The heat death is the quietest possible ending, a slow fade into stillness. The universe doesn't end with a bang or even a whimper. It just gradually runs out of the capacity to do anything interesting. Change becomes impossible. Another misconception is that the heat death could somehow be prevented or reversed. The second law of thermodynamics is arguably the most ironclad law in physics. While it's technically a statistical statement, the probability of a macroscopic violation is so infinitesimally small as to be effectively impossible. Entropy always increases in a closed system, and the universe as a whole is a closed system by definition. There's nowhere else for energy to come from, no external system to provide the order needed to reverse the process. Some speculative physics considers whether quantum fluctuations might, given enough time, spontaneously create order from chaos. On timescales of perhaps 1 to 20 years, exponentially longer than the timescales I've been discussing, quantum fluctuations might theoretically create temporary structures, perhaps even Boltzmann brains, conscious entities formed purely by chance from random particle arrangements. But these ideas are highly speculative and rely on extrapolating quantum mechanics to timescales and scales where we have no experimental guidance. There's something profoundly melancholic about contemplating the universe's ultimate fate. Everything we see, every star, every galaxy, every structure is temporary. Not just temporary on human timescales or geological timescales, but temporary even on cosmic timescales. The age of stars, planets, and galaxies is a brief flourish at the beginning of cosmic history, after which comes an eternity of darkness and decay. Yet there's also something strangely peaceful about it. The universe's story isn't one of violent destruction, but of gradual, gentle winding down. Stars don't all explode, most fade away. Galaxies don't all collide catastrophically, they drift apart. Even black holes don't persist forever, they slowly evaporate. The universe's end is quiet, patient, inexorable. What does all this mean for us, for life, for consciousness? On these vast timescales, biological life seems impossible. No stars mean no habitable planets. But some physicists have speculated about other substrates for life and thought. Could intelligence exist as patterns in degenerate matter, in the structure of neutron stars or electron-positron plasmas? Could computation occur in incredibly slowed-down processes that extract tiny amounts of energy from the fading heat of white dwarfs? Freeman Dyson explored these ideas in his 1979 paper, suggesting that intelligent beings might survive indefinitely by adapting to progressively lower energy environments, slowing their metabolism and thought processes to match the decreasing available energy. They would think more and more slowly, but could, in principle, think an infinite number of thoughts given infinite time, even as the universe's available energy approached zero. It's a beautiful idea, though probably not physically realizable given quantum mechanical limitations and the eventual evaporation of all matter. What's certain is that the universe will change beyond recognition. The cosmos, in 100 years, will be as different from today's universe as today's star-filled cosmos is different from the hot, dense soup of particles that existed in the first microsecond after the Big Bang. We're living in a special time, the brief era when stars shine, when complex chemistry is possible, when energy gradients allow for the emergence of structure and life. Have you ever felt a sense of urgency, a feeling that time is limited and precious? On cosmic timescales, that intuition is profoundly correct. The universe's age of vibrancy, complexity, and possibility is temporary, already well underway, and will someday end. We exist during a rare and precious epoch, and, in a real sense, we're watching the universe in its youth, full of energy and potential that will gradually, inevitably fade. But endings aren't just about loss, understanding the full arc of stellar death. From the final moments of a dying star through the creation of stellar remnants to the ultimate fate of those remnants over cosmic timescales reveals something profound about existence itself. It shows us that death and transformation are woven into the very fabric of reality, operating on scales from individual stars to the universe as a whole. And in recognizing this pattern, this cycle of birth, life, death, and gradual return to simplicity, we might find insights not just about the cosmos, but about our own place within its vast story. We've traveled together through an extraordinary journey, from the final heartbeats of dying stars to the ultimate fate of the universe itself, spanning timescales from seconds to 100 years. We've witnessed supernova explosions that briefly outshine galaxies, explored neutron stars where matter is compressed to its absolute limit, peered into black holes where space-time curves back on itself, and contemplated a far future where all stars have faded and the cosmos settles into eternal darkness. But now, as we come to the end of this exploration, I want to step back and ask a deeper question. What does all of this mean? What can stellar death, occurring across unimaginable distances and time scales, possibly teach us about our own brief existence on this small planet? If this journey has moved you in any way, I'd be deeply grateful if you'd take a moment to like this video and subscribe to the channel. Your support allows us to continue exploring these profound connections between cosmic phenomena and human understanding. The first and most striking lesson from stellar death is one about impermanence. Nothing lasts forever. Not stars, not galaxies, not even black holes. The Sun, which has illuminated Earth for 4.6 billion years and seems eternal on human timescales, will someday swell into a red giant, shed its outer layers, and fade into a cooling white dwarf. Betelgeuse, that bright red star marking Orion's shoulder, could explode as a supernova tonight, next year, or 100,000 years from now. But its fate is sealed. Even the most massive black holes, those cosmic monsters that seem to devour everything around them, will eventually evaporate through Hawking radiation, given enough time. This cosmic impermanence mirrors a fundamental teaching found in Buddhism and other contemplative traditions, the concept of anitya, or impermanence. Everything that arises will also pass away. Every phenomenon, from the briefest thought to the longest-lived star, is transitory. The Buddha taught that suffering arises from our attachment to things we wish would last forever, our resistance to the natural flow of change and dissolution. When we look at the universe through the lens of stellar death, we see this teaching written large across the cosmos. Stars don't cling to their hydrogen fuel, trying desperately to maintain their main sequence existence forever. They burn through their resources, transform, and die, often giving birth to new elements and new generations of stars in the process. There's no resistance, no struggle against the inevitable. There's simply the unfolding of physical processes according to natural laws. And yet, in that inevitability, there's profound beauty. A supernova explosion, while representing the death of a star, is one of the most spectacular events in the universe. The Crab Nebula, the remnant of the 1054 supernova observed by Chinese astronomers, isn't a tomb or a tragedy. It's a luminous, expanding shell of gas and dust, seeded with heavy elements, illuminated by the pulsar at its heart, a testament to transformation rather than ending. The planetary nebulae created by dying sun-like stars are among the most beautiful objects visible through telescopes, each one unique, displaying intricate structures shaped by magnetic fields, stellar winds, and the complex physics of the star's final stages. When we see these nebulae, names like the Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, we're not looking at death, but at transformation, at matter returning to the cosmos to eventually form new stars, new planets, perhaps new life. This brings us to the second profound lesson: death as transformation rather than ending. When a massive star explodes as a supernova, it doesn't cease to exist. Its matter scatters across light years of space. Its elements mix with the interstellar medium. And over millions of years, that enriched gas collapses under gravity to form new stars. Some of those stars will have planets, and on at least one of those planets, carbon, nitrogen, oxygen, phosphorus, and sulfur, elements created in previous stellar deaths, assembled into molecules complex enough to replicate, metabolize, and eventually evolve into conscious beings capable of contemplating their own origins. You are not separate from this process. You are this process. The atoms in your body are ancient, forged in stellar cores billions of years ago, scattered by supernovae long before Earth existed, incorporated into the molecular cloud that formed our solar system, gathered into the planet we call home, cycled through countless organisms over billions of years of evolution, and temporarily assembled into the pattern you call yourself. When you die, those atoms don't disappear. They return to the Earth, eventually dispersing back into the environment, becoming parts of other organisms, other structures. On geological timescales, some of those atoms might be subducted into the Earth's mantle, later erupting from volcanoes. On cosmic timescales, when the Sun becomes a red giant in about 5 billion years, any atoms that were once part of you might be vaporized, becoming part of the planetary nebula the Sun creates, eventually mixing with the interstellar medium to potentially form new stars. There's something both humbling and comforting in this perspective. Your individual existence is temporary, yes, but you're part of something vastly larger and older, a cosmic cycle of matter and energy that's been operating for nearly 14 billion years and will continue for trillions of years into the future. Death isn't an end, but a transition, a change of form, a return of borrowed atoms to the cosmos. The third lesson from stellar death is about scale and perspective. We humans have a natural tendency to see ourselves as the center of the story, to view our concerns, our time scales, our spatial scales as the important ones. But the universe operates on scales that dwarf human experience to the point of absurdity. A human lifetime is roughly 80 years. A stellar lifetime ranges from millions to trillions of years. The distance to the nearest star is about 4 light years, meaning light takes 4 years to traverse it. The distance to the Andromeda Galaxy is 2.5 million light years. The observable universe is about 93 billion light years across. And as we've explored, cosmic timescales extend to 10 Monagers 100 years and beyond. Numbers so large they're essentially meaningless to human intuition. Contemplating these scales can induce what researchers call the overview effect, a cognitive shift reported by astronauts who see Earth from space. Personal concerns and conflicts suddenly seem petty when viewed against the backdrop of the cosmos. National borders are invisible from orbit. The distinctions we draw between groups of humans seem arbitrary when you realize we're all equally made of star stuff, all equally brief patterns in the cosmic flow. This shift in perspective doesn't diminish the importance of our individual lives or our immediate concerns. Pain is still pain, love is still love, joy is still joy, regardless of cosmic scales. But it does provide context. It reminds us that the universe doesn't care about our anxieties, our deadlines, our social status. Stars don't explode because we were good or bad, neutral or evil. Black holes don't evaporate faster or slower based on human morality. The cosmos operates according to physical laws that are indifferent to our existence. And there's liberation in that indifference. If the universe doesn't inherently care, then we're free to create our own meaning, our own values, our own purpose. We don't have to live up to some cosmic expectation or fulfill some predetermined role. We're temporary patterns of organized matter, briefly conscious, free to choose what matters to us during our brief time of existence. The fourth lesson is about interconnection. Stellar death reveals that nothing in the universe exists in isolation. Every element in your body, except hydrogen and some helium, was created in a star. Those stars, in turn, formed from gas clouds enriched by previous generations of stellar deaths. Those earlier stars formed from the cooling aftermath of the Big Bang, structured by quantum fluctuations in the first fractions of a second of cosmic history. You are connected through an unbroken chain of physical causation to the birth of the universe itself. More immediately, you're connected to every other living thing on Earth through shared biological ancestry and shared atomic heritage. The oxygen atoms you breathe out might be inhaled by someone on the other side of the planet. The carbon atoms in your cells were once in dinosaurs, ancient trees, bacteria, other humans throughout history. This interconnection extends temporally as well. Future generations will be made of atoms that are currently part of you, part of the Earth around you. The actions we take now, the carbon we emit, the nuclear waste we create, the ecological changes we trigger, all of these will affect conditions millions of years into the future. We're not separate from deep time, we're embedded in it, connected to both the deep past and the distant future through the physical continuity of matter and energy. The fifth and perhaps most profound lesson is about meaning in a finite existence. The universe, as far as we can tell, will eventually reach heat death, a state of maximum entropy where no complex structures can exist, where essentially nothing happens anymore. On the longest timescales, all stars will die, all structures will decay, all information will be lost. Everything we do, everything humanity achieves, every civilization that ever exists, will eventually be erased by the relentless increase in entropy. This can sound depressing, even nihilistic. If everything ends, if nothing lasts, what's the point? Why does anything matter? But I'd invite you to consider an alternative interpretation, one that finds meaning precisely in finitude. A sunset is beautiful partly because it's temporary. Music is moving partly because each note passes away, making room for the next. Life is precious partly because it's finite. If we live forever, if stars shined eternally, if the universe existed in a static, unchanging state for all time, would any moment be special? Would anything have significance? Impermanence creates value. The fact that stars die means that starlight is a gift, not a guarantee. The fact that life is temporary means that the present moment, this breath, this experience, is irreplaceable. You will never live this particular moment again. This configuration of atoms and energy that you call yourself will exist only briefly before dissolving back into simpler components. That's not a curse. It's what makes your existence meaningful. The Japanese aesthetic concept of mono, no aware, captures this beautifully. It's often translated as the pathos of things, or an empathy toward things, describing a sensitivity to the transience of existence and a gentle sadness at their passing, coupled with a deeper appreciation of their beauty precisely because they don't last. Cherry blossoms are treasured in Japanese culture, not despite their brief blooming, but because of it. Their beauty is inseparable from their impermanence. Stellar death teaches the same lesson. A supernova is spectacular partly because it's rare and brief. The age of starlight is precious precisely because it's temporary. We exist during a special epoch in cosmic history, the brief time when stars shine and complex chemistry is possible. That's not something to mourn, it's something to appreciate. Now, as we bring this journey to a close, I want to leave you with a thought to carry into your own life. Tonight, or whenever you next have a chance, go outside and look up at the stars. Find Betelgeuse in Orion's shoulder, that red supergiant that could explode at any moment. Find Sirius, the dog star, with its invisible white dwarf companion. Find the Andromeda galaxy if you're in a dark location, that faint smudge of light that's actually a galaxy of hundreds of billions of stars, many of them already dead, their light still traveling toward us. When you look at the night sky, you're not just seeing distant points of light. You're seeing a graveyard and a nursery, a place where stars are constantly dying and being born, where matter is cycling from simplicity to complexity and back again, where the elements of your own body were forged billions of years ago in processes so violent they briefly outshone entire galaxies. You're also looking backward in time. The light from Betelgeuse left that star roughly 500 years ago, during the Renaissance on Earth. The light from Andromeda has been traveling for 2.5 million years, since before humans existed in our current form. When you look at distant galaxies through a telescope, you're seeing them as they were billions of years ago, perhaps looking at stars that have already lived and died, their final light only now reaching your eyes. And you're looking at your own origins. The story of stellar death is your story. You are the universe's way of knowing itself, atoms arranged in such a way that they can contemplate atoms, a process spanning 8 billion years culminating in this moment of awareness, of understanding, of wonder. There's a beautiful symmetry to this journey we've taken. We began with the final moments of dying stars, those desperate attempts to maintain fusion, to hold off the inevitable collapse. We end with a reflection on our own mortality, our own impermanence, and the meaning we create in the face of universal entropy. Stars teach us that endings aren't separate from beginnings, that death is woven into the fabric of creation, that transformation is the fundamental nature of reality. Carl Sagan said, "We are star stuff," and that's literally true. But we're more than just star stuff. We're star stuff that has organized itself into patterns capable of wonder, of curiosity, of compassion. We are the universe's way of reflecting on its own nature, brief eddies of complexity in the cosmic flow from order to disorder, temporary islands of consciousness in a vast sea of unconscious matter and energy. And perhaps that's enough. Perhaps meaning doesn't require eternity. Perhaps significance doesn't depend on permanence. Perhaps the fact that we exist at all, that atoms forged in ancient stellar cores have assembled into beings capable of contemplating their own origins and fate, is itself the miracle, the gift, the meaning we've been seeking all along. As you lie down to rest tonight, as your consciousness gradually fades into sleep, consider that you're participating in the universe's greatest story, one of constant transformation, of endings that are also beginnings, of death that enables life. The atoms in your body have been recycling through the cosmos for billions of years. They've been inside stars, inside other living things, inside the earth itself. For a brief moment, they're arranged into the pattern you call yourself, conscious and aware, before eventually dispersing back into the cosmic flow. But while they're arranged in this particular pattern, while you exist in this brief window between birth and death, you have the extraordinary privilege of being aware, of understanding, of appreciating the vast and beautiful universe that created you. You can look up at the stars and know what they are, how they work, where they came from, where they're going. You can feel awe at the immensity of space and time. You can find meaning in the temporary, beauty in the impermanent, significance in the finite. Thank you for taking this journey with me, from the final moments of dying stars through the creation of elements, the formation of stellar remnants, and ultimately to the heat death of the universe itself. I hope it's given you a new perspective on death, transformation, and the preciousness of existence. Rest well, knowing you're part of something ancient and vast, a cosmic story still unfolding, written in the language of physics across billions of light years and trillions of years. Sleep with the peace that comes from understanding your place in that story, temporary but real, finite but meaningful, a brief flame of consciousness in the cosmic darkness. And when you wake, I'll be here with new stories to explore, new mysteries to unravel, new journeys to take through the infinite wonders of our universe. Until then, sweet dreams, and may the stars watch over you.